That's super satisfying. Oh my god. Let's see. You got them all level? Okay.
He's got no break.
Oh dang. The Reddit's had great. Oh no.
They don't because he's such a bum. Tell me.
And then
He's only down. Look,
Where the hell Ava go?
so he only damn little people. Like what you mean by that?
like, he's down somebody like, I'm saying the people he want now. He want down nobody
Like Ian,
yeah. And,
Alliance.
JT, Elijah. He won't need them Pierre. And then down somebody like Ethan, me, TJ, Cody, Ruben, Braden,
Doing what?
Papa,
Oh yeah.
Dave.
Look, I walked up yesterday. I got you, Deuce.
Well, I'm
Yeah. I got you good, boy. Bro, do what? Say I run a post corner, and I went in, hard step, jabbed out, and I just lost. Dude lost me.
You do play corner?
Yeah.
I feel like if Deuce grow,
Deuce got 5 corner.
yeah, I feel like if Deuce and TJ grow, and by junior year, bro, we're gonna have a loaded line, bro. I feel like if Braden is alright, oh my god, we going to state. Oh my brother, we going to state. I swear.
What the hell? Mr. Anderson. We all ran out of shit.
Oh fuck!
Ran out of what? I got orange shit.
You had 3 bags in there.
Oh, fuck. You got it. I gave one to someone. And then.
He gave one to the girl.
He had one to Laura.
Laura ain't here.
Laura?
Yeah, Laura.
Right here, bro.
I didn't get any to her yesterday.
For a bit, don't be bullying now. Like 3 or 4.
I'll give you 2.
No, I need 3 or 4. I need
1, bro.
I need 3 or 4. That way you don't pull me over.
So it can hold you over.
I ain't going to see. I had to roll and run yesterday because it's not.
Oh, God. That's it.
As a that was
Why you going so slow?
I didn't want to do this shit.
When you start out so fast, then soon I got to the other side.
I see.
Cause I was getting dizzy, bro. Cause you see, I work a straight line and I go like this. I was getting dizzy, bro.
Bro, on me. I saw Shania here and Dre right here. I was like, what the
Cause
hell?
look, I had a roll and run. And when I was rolling and I got up, I was dizzy, so I was seeing like this.
Cause it's 5 minutes.
They had me dead. I was freaking dying. I'm not
We
laughing.
didn't get up until we got done catching.
No, I didn't.
Yeah.
Cause I was on the ground.
Yeah, no time. You was on the ground.
Yeah, but I was done rolling though.
Where you
Yeah, I was done rolling. I was like,
You was on the ground for 5 minutes.
That's bro. I ain't never had a roll and run a day in my freaking life.
Oh, we can tell.
You never know.
That thing got did that. I could see him roll and roll. God dang.
Like,
Oh, shoot.
I'm rolling like this, and then my damn body is turning.
Shit, then roll. Yeah. Shit was fun. I didn't laugh. I did. It was fun. Let me read.
I'm gonna tie my hair down. You ready? Look.
I'm going here and fun.
Oh my god, I gotta go get a comb and then this again.
You said 2 or 3. 2.
I said 3.
You said 2 or 3 right then, boy. Be one more.
2.
1.
2.
1. 1 and done.
That's Terry, bro. I swear to God.
1 and done. Go.
Oh, I don't know. Hey, you got another ruler over
Nah.
Ruben,
Run out the day again. Yeah, I mean, the third period. No more, bro. 1.
I said we were losing test today.
Oh, Mr. Wilson said it's not today, it's Thursday. Thank you, Lord.
test for what?
I tell you, it's a test on the 88P. It's today.
No, it's not. It's Thursday.
All right, say, it was a goal.
I'm walking outside.
Yeah.
Can't move your pants with it.
What? No, I'm not talking. What? Say, I'll never be annoying. God damn it. I'm associated with her in no type of form, but she didn't know how she was talking. Like, no. I say that's the thing.
Oh yeah.
I don't know you, I don't know you, you don't know me. She be like that. Like, what's this?
I said, Timmy, look at Whistler. Look at it. Let's listen to this.
Devin,
Yeah.
splash.
Oh, you never did this now? In the park?
Our seventh period didn't get to do that. She said we don't have to do that.
Where'd you go, April?
We had
Yeah,
no
we were just
tea
talking
time.
outside.
Hey, you know, I'm not.
Are you talking about? I didn't tell you.
Splash. You know, I'm not.
Is that what it is?
I can't say.
Well, I've already been told.
What are we talking about?
Nothing.
We need something right now. I'm
No, but I know what you embrace again.
Hey, what am I doing?
Hey, KP.
What?
No,
Hey,
it-
Jay.
You see the things that I made?
Okay.
I did that one.
no, Ava, don't ever. Like, no, you. No, you gotta.
Ready?
You don't have to do Mr. Kim. Yes, you do.
We don't want we're practicing our dolphin here today in weight room.
What is CP? Like, what does that stand for?
Chris Cochran loves it.
Who like the other one?
And guess what? I don't have detention today.
Bitch, lady sucker.
Yeah. She took it away.
You're happy.
Oh, shit.
Yeah, because Chris Cochran emailed a picture of this of us squatting. But she told me and Laura are gonna have to lift this one day in her class. Show her she's right.
I'm not care if they do this.
My goddamn head. I ain't supposed to walk above my head. It hurt.
Good morning, it's a great day to be a Viking. Just a few reminders about Naviance. If you would like to sign up for college visits, they will be tomorrow. Also, 40 Days of Life is a prayer campaign that aims to end abortion through prayer and fasting. So Thursday from 3 to 4. Please try to come by and just say a prayer outside. We would love to have lots of our Vikings out there to come by and say a prayer for all the moms who are in really a hard place. And in life, Vikings, that sometimes happens. lunch. And then just think what happens to your productivity after lunch. Or if you want to spend a little time in the morning, or maybe your teacher will take you out. So try that and let's watch the productivity go straight up. Please stand for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation under God, indivisible, with liberty and justice for all. And now, if we quiet ourselves to get the presence of God, our beautiful morning prayer today, Vikings, is the Hail Mary. In the name of the Father, and the Son, and the Holy Spirit, amen. Hail Mary, full of grace, the Lord is with thee. Blessed art thou amongst women, and blessed is the fruit of thy womb, Jesus. Holy Mary, Mother of God, pray for us sinners, now and at the hour of our death, amen. Now, Vikings, lift up to God anyone you feel called to pray for today, asking God to bless and guide them. In the name of the Father, and of the Son, and of the Holy Spirit, amen. Have a great day, Vikings. Make the day full of joy. Be kind to each other. Be especially kind today. I'm someone that you're going to say, you know what, I don't know this very well. I'm going to be kind. Have a great day, Vikings.
All right, let's see. Peter, Natalia. What? Speak quiet. Gavin.
Yeah.
John.
Yeah.
Miguel.
Yeah.
Trey. Dion.
Right here, coach.
Rashawn. It's outside. River. Elijah. Ava. Carl. Travis. Caroline. TJ.
Here.
Trey.
Dean Wilson, can you please come to the high school office? Dean Wilson, come to the high school office.
All right. So we're talking about cycles. All right. And there's lots of cycles. One of the ones that stays in the news because of global climate change that you hear about all the time is carbon. Carbon cycles. Carbon cycles all the time. And
Jump.
y'all settled in. Y'all should take care of that already. All right. Carbon constantly cycles. And of course, going back to CO2, you hear about, like I said, it's one of those things in the news all the time. Of course, carbon is so important. Every living thing, that if it didn't cycle, it would cause a lot of problems. If all of a sudden we shot all the carbon into space, well, they have a hard time living, right? Because we know that carbon makes up carbon dioxide. We know we need it for glucose. We need it for proteins. We need it for fat. Makes up all of our macromolecules. All right? Carbon's in the atmosphere is CO2. Makes up a very small percentage of the atmosphere. Alright, so it's all around us. Now, where did the carbon come from? Alright? Well, most of it was released rock. Right? It was released from the rocks, from volcanic rocks, into the atmosphere, and the trillions of tons. Some of it is released from rocks that are exposed to sunshine. Volcanoes, heat, all right? It causes carbon to be released in the atmosphere.
What about the ones on the ocean?
Yep, those two. Carbon, the carbon that is released from them has got to go somewhere, so it goes into the ocean. Sometimes it is released as carbon dioxide, all right? And it releases CO2 into the atmosphere. For a long time, Earth had a lot more carbon dioxide in the atmosphere than it does now. There's still a significant amount of CO2 in the atmosphere, but as a portion of our atmospheric gases, it's much smaller than it used to be. It's heavier than oxygen and nitrogen. It also traps energy more than oxygen and nitrogen. If it gets out of control, if the balance is upset too much, then it could cause temperature changes globally. Now, CO2 in the atmosphere initially was much heavier than it is now. But once plants began to use it, all right, and pull it back out, plants started releasing oxygen, right? So the plants released the oxygen, kept the carbon, and that's through photosynthesis. Right? They were kicking out oxygen molecules. Now, from a geological perspective, this changed the whole planet. There may have been a time that other planets near us, Venus and Mars, had significant amounts of oxygen on them and significant amounts of carbon dioxide on Mars, less carbon dioxide on Venus. But Earth has been able to hold on to its oxygenated atmosphere, even though it's only 21% of the air we breathe. All right? Most of the air that we breathe is nitrogen. Second most common gas is oxygen. And then after that, carbon dioxide makes up less than 1% of the atmosphere. So it's not that much. But the plants pull the carbon dioxide out. They kick the oxygen back in. That's how we breathe. Alright? So fairly important stuff. Now, you can't keep the carbon, can't keep it. Alright? It has to cycle back in. Now, glucoses are taken in by the consumers. Alright, and this will make our primary consumers. We'll make this our primary consumer. This is our first level consumer. This is our cow. This is our herd animals. These are our buffalo. This is our grazing animals that go around grazing, eating grass, elephants. All right? It's our primary consumer. Now, the primary consumer breaks down the glucose. When the primary consumer breaks that glucose down, it uses oxygen. So the oxygen comes back out of the atmosphere. We put O2 in, and we release some of the CO2 back into the atmosphere. So it's going back. So we're pulling some of the oxygen out. Our primary consumer is using it. And metabolism all right, these up here. Metabolism heat and carbon dioxide. You need to go sit by yourself again. Sitting there dancing at your desk is distracting everybody around you. So, stop. It's okay to dance at your desk. You just can't do it when you're sitting around everybody else. Alright? If you're going to do that, you need to go back where you're not around other people. Alright? Now, all that heat and everything, carbon dioxide, cellular respiration pulls it back out. Then primary consumers, well, they get eaten by our predators. Scavengers. Etc. And they have metabolism, heat, cellular respiration. That puts more carbon dioxide back into the atmosphere. All right? So it's constantly going back in. Now, with all of this carbon out there, it's important to understand this is the primary reservoir. All right? CO2 in the atmosphere. Is the primary reservoir of carbon. just like our oceans are the primary reservoirs for our water, the atmosphere is our primary reservoir for carbon. That's where most of the carbon on the planet is. It's in CO2 in gas form in the atmosphere. It's also stored in living material. When we say living material, we're talking about you. Everything that's alive. All right? We also have carbonate rock. Now, this goes back to a concept we kind of touched on yesterday, and we'll keep coming back and touching on this from time to time. Matter's not created or destroyed. It can change forms, but we don't create it or destroy it. It's always there, somewhere. Sometimes there's more carbon stored in rock in Earth's history. Sometimes there's more carbon in the atmosphere. Sometimes there is a significant portion in the plant life and animal life of Earth. A lot of times we will get into, I don't know, let's see, how should I put this? We'll get into issues with carbon. God. A lot of times we will get into issues with carbon that get out of balance. We could potentially release too much carbon dioxide into the atmosphere, either through volcanism, through industry, through I can't hear you. The clock what?
It's the clock happening now.
Put your mask on. I'd have to say more on that. And people, you know, like I said, people will get into issues with it. Truth is, carbon just cycles. Have humans significantly changed the climate? Yes. Is it going to kill everybody? Probably one of these days. Is there anything, you know, is there anything unnatural about that is the question, I guess. No, not really. Every species that's ever existed will go extinct. And that includes us. And, with what humans do, that it's just part of it. But there have been people, predicting the end of times for how many years? At least since the Great Floods, right? I mean, there's a great flood in almost every county. There's one in the Bible. There's almost every mythology has some type of great flood. The Epic of Gilgamesh. The great flood in Norse mythology. The great flood in almost all of them. And I guess the thing is, don't panic and just, there's always going to be something out there. That people are going to try to manipulate into money. And so far we've survived all of them. During my generation, of course, it was nuclear holocaust. Oh, they had something called the nuclear annihilation clock, and it was called DEFCON, and they would move the DEFCON clock. Midnight was when when nuclear holocaust was going to happen, and the Soviet Union and the United States were going to nuke each other into oblivion, and of course that's called the Cold War. And we pretty much went to sleep every night knowing that, we just knew the Russians were going to sneak up and nuke us in our sleep, and the world would all end in a giant fireball followed by a global disaster called the nuclear winter. And that was what was predicted. So there's always going to be something out there that people are telling you is going to kill us all. And we'll study a little bit about that when we talk about Malthusian economics. Thomas Malthus was an economist, and he said that there were basically populations that expanded exponentially until they got to a point where they could no longer manage their numbers. And of course, with humans, the things that he said kept human population down were disease, war, and famine. So, those were the population managers. I guess it depends on, where you want to look at it. Of course, the one that everybody's worried about right now is disease. We're all, trying to avoid the COVID, the corona, the novel coronavirus. Several years ago, it was Ebola. Ebola was the scary thing. So it's always going to be something.
Do they have a vaccine for what?
For what?
Do they have a vaccine for the corona?
No.
Are they inventing one?
Usually a vaccine, they keep promising it's going to come out soon. Vaccine usually takes about 5 years to test.
What the? 5 years of wearing these things?
Huh?
5 years of wearing these
No.
things? You already used to it. So cool.
Now, we'll get to herd immunity before that. But, they keep promising that it's going to come out in, 6 months or whatever, but let's just say I'm skeptical. It could, but, vaccines are not that easy to produce, and making one without that doesn't have side effects. I understand how vaccines work. They kick off your immune system. Well, if you kick off the immune system, you can also kick off other stuff. You give a kickstart to your immune system to produce a certain type of cell. Well, if you produce some types of white blood cells, you could cause other problems. It may be as deadly as the coronavirus.
Why did you want to make something that can cure all viruses?
Do what?
Like
I can't hear you.
they can make something that can just cure all viruses.
Well, there has been research into creating a universal vaccine, which basically would cause your body to be able to produce a wider range of white blood cells to fight off different viruses, different types of viruses. All viruses aren't the same. And your body produces specific antibodies to fight specific viruses. Well, since they're pretty much virus specific, and there's millions of viruses. And, we only talk about a few of them. There's millions. A universal vaccine is probably not right around the corner for us scientifically. Yes?
So, I was like, it was a long time ago. This is like, we was in 8th grade. So, when coronavirus first started coming to Columbus and stuff, and I started getting in the hospitals, they was saying that you could pay for like coronavirus treatment. Like, they get a 7-day treatment for like $7,000.
My son works in the hospital in Atlanta, Piedmont, Atlanta, in the CVICU. He's actually in the part of the hospital where they have the worst patients. They have some treatments that they can do. Most of the time, your best defense against coronavirus is your immune system. Your immune system is pretty powerful. Most of the people that get coronavirus don't die.
That's was like 2%.
Not even that, but like 1. 10% would be huge. 10% is a high mortality rate. All right? Somewhere between 1 and 3%. So the chances of you actually dying from it, not that high. As compared to something like Spanish flu, where it was about 30%. And that was back in 1918. But what we occasionally have, and that it's nothing new. Every year there's a pandemic.
What was the pandemic? 2018.
Flu.
2017.
Flu. We have a pandemic flu every year. Every year. The worst one between 1918 and now was probably Hong Kong flu. That was 1969. 1969, 1970. And it had roughly the same mortality rate as Corona. About 1 to 3%, maybe a little bit higher.
But like, what is it like? Where'd you get it from? Where could you get it from?
It's just a flu virus.
They just call it Hong Kong?
Yeah, every year there's a different flu. You got Spanish flu, bird flu, swine flu.
Pigeon flu.
Okay.
And you can't do all those.
Yeah, they're still out there. Listen, diseases don't just go away. Once they're out of the bag, they're out of the bag.
Is Ebola still out there?
Yeah. Yeah.
Yes.
Yes.
I just Googled it.
Bubonic plague's still out there. They're all still out there. Okay? We have bubonic plague outbreaks in the United States every year. Now, that usually only involves 1 or 2 patients because, first of all, it's easy to treat now. Bubonic plague. The thing that killed about half of the world's population in the 1400s. Okay? It's easier to treat, and we know how it's spread. Whereas, Ebola, Ebola's still out there. And I'd have to look it up on the CDC. I'd be willing to bet there's probably an Ebola outbreak somewhere in Africa right now. There seems to have been one about every 4 to 5 years.
Is there any type of disease or illness that's still like that was like there in like 1400s and still continue to be down?
Yeah, they're all out there. They don't, like I said, they don't go away. We just are able to fight them.
How about black plague?
It's still there. That's what bubonic plague is. Still out there. People out west get bubonic plague.
So you die from it?
Yeah. You don't get treated.
What's the mortality rate?
Not that high. Why? Why is the mortality rate as high now as it used to be? Well, first of all, everybody alive today has ancestors that lived through it. So there is some genetic immunity, some genetic immune response that gets passed down. All right? Similar to Ebola also. I mean, Ebola started out with an almost 100% mortality rate. Diseases with a 100% mortality rate don't last very long. They kill all their victims and then everybody's dead and then it doesn't get passed around. Mortality rate for the last couple Ebola outbreaks has been 80s and 70%. Diseases get less virulent. Plus, people that survived the first time obviously have stronger immune systems. Now, has Ebola broken out in the United States? No. Not yet. Could it? Yes. Do what?
Not yet.
Not yet.
They got a cure for it?
No. It's a virus. I mean, you have to create a vaccine. There's actually scarier diseases out there than that.
In Colombia?
In the United States.
What's the scariest?
Probably hantavirus.
What is hantavirus?
Hantavirus comes from rats and mice.
So like you get bit?
No. Comes from their droppings. And what happens is rats always follow food. So the rats and the mice, I think it's a fairly specific mice out west, they get in food storage facilities and of course they eat through the cardboard and then they poop on the tops of the cans. And the rat droppings on the tops of the cans, people eat the food and don't clean the lids off. And they get hantavirus. And hantavirus is deadly.
Yeah, so I think
It's a 60-70% mortality rate.
You eat rat food.
so basically they'll go through the can, right? They'll eat through the can, do it.
No, they don't eat through the can. They eat through the boxes.
And then they poop on the can.
Right, on the can lids.
So see, now every can I get, I gotta wipe the top off.
I would. You should. Yeah. I mean, that's advisable.
He really got me worried, though. I'm not gonna lie. All these guys is like, I'm scared.
Here's the thing. There's no reason to worry. Because, I mean, if it happens, it happens. If it doesn't happen, it's not going to happen. The best defense you have in all of this is not your mask or your disinfectants or anything like that. It's your immune system. Your immune system is your best defense. Taking care of your immune system, eating right, exercising. Those things matter as much as anything. That's going to determine, the survival rate, your individual survival rate. Because like I said, once it's out of the bag, once the genie's out of the bottle, you're not putting it back in. It's in the long history of man versus viruses. It is viruses 7 billion something. Yeah. Humankind won. We've beaten one virus
Which one was that?
ever, smallpox. Smallpox is the only disease we've ever been able to eradicate. Everything else is still out there. Now we've reduced the numbers. We have significantly reduced measles, mumps, rubella, yellow fever, polio.
I don't think you can't polio anymore.
Okay? You can. You can. It's still out there. It's rare.
Oh, okay.
But because we've all been vaccinated, there is some herd immunity. I mean, you were first.
Oh no.
Oh,
Polio is
Polio, is that where your leg like paralyzed?
causes, yeah.
Yeah,
But it's still out there. Yeah, it hasn't gone away. The only disease that's been eradicated is smallpox. Which is a big win now. Smallpox is a big win. But, you know, it's still out there. Coronavirus is gonna be out there forever. It's not, it doesn't go away.
They said that it was a Chinese scientist. And two things actually. They said that it originated.
We don't know. Honestly, I don't think they have any idea where it originated.
And then one of them, and they said that our president, he let a Chinese scientist who had COVID probably, and that's how it started spreading like that.
There's probably about 0 facts in what you just said.
Probably is.
Yeah.
I ain't even gonna lie to you.
People will say anything just to make and especially today in this world of just stupidness.
Why
You
did
know?
people,
Stupidity.
if not going away, why did you want to let it well out, man?
Well, you don't want mass infections. Anytime you get a large quantity of cases, you increase your chances of death because you have less ability to treat active cases. And you overwhelm your hospital system. That's what happened with, that's one of the big things that happened with Spanish flu in 1980. It spread so quickly, it overwhelmed the system. And people were dying in their houses before they could even get to the doctor. The doctor couldn't get to see them to give them any kind of help. So, the point is that you don't want a huge number of infections in any one place at any one time, because it takes away your ability to deliver health care to those people. And that's an important part of it. Because if you can't deliver the healthcare system, if you can't deliver, the medical needs that are there,
How would they know that they died of the coronavirus?
that's just the blood. And I mean, a healthy individual's chances of dying are very, very slim. And when I say very slim, I'm saying 1% or less. If you have compounding problems, diabetes, overweight, cardio problems, you smoke, any extraneous, any other health problems always add to, the chance that something's going to kill you. And I mean, and smoking's a big one. That's my son. Like I said, my son works in the CVICU at Piedmont, Atlanta. A large percentage of the deaths that they have are smokers. That seems to be one of the biggest comorbidities that you can have. Smoking. Yes. But diseases are here and they don't just go away.
No, we leave it.
Yeah.
We cool.
Stick to.
Yeah, all right. I keep going.
What what's like the most deadliest disease like, in the world now?
The disease that's probably killed the most people is probably tuberculosis.
What is that?
Wait, wait. Never mind.
Can I get another?
Tuberculosis is a bacterial disease that attacks your lungs.
Can I get another map? Can I get another map?
Oh, so they was talking about
Tuberculosis, did you,
if you're over
why are you
60
getting one of my
years-
masks? I thought you were gonna get your own.
If
Yeah,
you're,
you can have one of mine, go ahead.
if you're over 60 years old, you have tuberculosis. Y'all do that commercial?
That's what you think is, man.
Yeah, tuberculosis, kills you slowly. They used to actually have TB wards, and they would put people in something called an iron lung.
Oh, yeah.
But tuberculosis, spreads on your, put your mask up. Tuberculosis spreads mostly through spit. There used to, and that's why it's actually illegal to spit on the sidewalk.
That's up.
Oh, it is?
Okay.
It's illegal.
You said it was up.
Spit. Like,
Spit on the sidewalk.
Wow.
Spitting is what spread tuberculosis back in the 1800s and 1900s. So, spitting on the sidewalk in a lot of states is actually illegal because that's what spreads it. TB is a bacterial disease. Now, it's not a virus. It's a bacteria. And we could treat a bacteria with an antibiotic, except for people that were in Russian prisons called gulags.
Welcome to the gulag.
Got sick with TB, and instead of treating them the way they're supposed to, they only treated them until their symptoms went away. And that means that all the tuberculosis was not gone, so they kept having to retreat them. Well, they basically created a tuberculosis that was antibiotic resistant. And then when the Soviet Union fell and broke up, and they let all the prisoners out of the gulags, it was out there. They've actually isolated most of the cases of it, of the antibiotic resistant tuberculosis. But I mean, we've created some diseases that are pretty scary. Actually, some sexually transmitted diseases that are pretty scary because they don't have a cure. Okay? Other than HIV, of course, we know there's no cure for HIV. But you know, there's some STDs that they're antibiotic resistant.
Sorry, question.
Yeah.
So you know how if you have HIV or sexually transmitted disease, the person that you have, like, you know, like the person that you can, you know, I ain't gonna say it. Like, don't you gotta let them know that you got it? Don't you gotta let them know that you got HIV? And cause they get it and they die. Are they gonna charge you for murder?
Nope.
You the one who wanted to do it.
Yeah.
Better watch it. Your thing.
Individual responsibility.
They ain't gonna
But like I said, there's a lot of diseases out there that we can't do we really can't do anything about other than protect ourselves. You know, tuberculosis is probably the all-time leader. I read at least one scientific report that said tuberculosis may have killed up to 7% of all humans that ever lived. That's a lot.
How much
Okay.
is that population?
Huh?
How much is like that?
Well, there's been 14 billion people alive in the world, ever. 7% of that is what? 14 billion. 10% would be 1.4 billion. 7% would probably be right around a billion. Billion two, yeah, somewhere right there. There's a lot of people. But like I said, You know, it's out there. It's one of those diseases that we can treat if it's not one of the forms that's antibiotic resistant. The antibiotic resistant ones can't do anything about. Y'all heard like MRSA? Y'all know what MRSA is? It's a staph infection that you can't treat. You have to go in the hospital and they give you vancomycin. There's actually one called vancomycin resistant staph. It's even worse. It's rare, but it's out there. And you know, it's one of those things that, you know, staph infections are all around. People have gotten staph infections and their sinuses, and that's never good, especially if they're antibiotic resistant. Not stuff you want to have. Okay. But there's always something. It's always carbon emissions, or volcanoes, or comets going to hit us, or Russians are going to do this. It's always been something. So, you know, the end of the world is not. Yeah, the end of the world coming is not something new to this, you know, society or our society or our country or anything like that. It's not something that's, you know, since the beginning of time, since the beginning of written history, somebody has always said something was going to cause the world to end. Y'all need to start remembering to put your book bags in the back. I've got like, looks like 1, 2 people did what they were supposed to do today.
You don't need nothing but time to go.
So y'all need to start remembering to do that, please. I will remind you tomorrow. All right, let's clear it off so I can clean it down.
Dirt bag. I'll give you one today.
You see that TikTok? That girl's running around.
Hey, watch the figure I said. Where?
Yeah.
Oh, I got like 10 pounds.
Here, Sean.
Einstein.
Show me what you look like. Oh, show me what you look like.
You know,
It's not even my business. I have to look down.
yeah, good. You have to make adjustments. I'm taller than that.
Forgot my color right now.
I was sitting on the toilet. I had to take
I know y'all heard that. You know you heard that, right?
You've been on TikTok anyway. I think you need to delete TikTok.
Yeah, for sure.
Go like, I clear my shoulders off.
Wait, for real?
No, please stop. Stop. Please stop. Please stop. Stop. Yeah, that's what I'm
You can stay down. You can. Oh no, I found him on. I found him myself.
There's no
At the park. They're at the park.
See that, man.
I was sitting
Why
on
do
the
you
toilet. I had to
It's sad time to do it.
Trump, yeah, hey.
Mine's loud. Yeah, this is also sad.
No, I already know. That's what we're talking about all morning. So is that right or no?
What?
Yeah, it is. There was anything else to add to it? Nothing.
You told me right now. You told me right now. You got 30 seconds. One.
I know that. No.
Don't walk that way.
No, I want everybody.
Yeah,
Okay, once I figure out
See the hospital?
Tell me.
Peter, don't try me. Oh, almost smacked me. You got this water line.
Yes, that's my move back. That's my well, I'm at guess, but I'm not gonna guess. Water's never been out.
Yes, y'all have a nice day, stay out of trouble.
Don't do anything stupid.
Don't do anything stupid.
I look forward to that every day.
Yeah, that's exactly like it.
Oh my God, it's straight booty.
My dog, she a big over. Somebody dog does.
I meant like ours. Mia, your lunchbox was in my air drink. She wanted me to tell you. I didn't think you were throw that at me. I was like, you're the one gonna get your thing, right? Yeah, I have one.
That's crazy.
Yeah, I don't, but yeah, I'll take that. I'm like, he's old. You got
How's Tesla?
Okay, bro.
my partners are in SCG, so
You said that yesterday.
Because Dollar was there.
Well, sounds like you're not gonna get it done.
That's how we're I am already to do this.
Oh, yeah, but it's gotta be.
There was nobody in there.
It's easier for me to get it here. All y'all, everyone else is testing?
Yeah.
First time was actually.
Hey, Mia, I have a question.
How do you call it,
Mia,
Cause
do
it's,
you know if
Wi-Fi network
Eddie
it's not fun.
I was just wondering if he's gonna be my third period, because I'm like, there's only the three of us, so. And I know for a fact Caleb and Solo are not taking SAT. What? Yeah, I knew that, I know. No. You got me wrong. Wait, did you just raise your phone?
Research paper.
The history of Tesla stock.
I'm so
The history of Tesla stock.
I
What video are you on, man? There'll be other stuff on there?
Yeah, she's gonna put a picture of the football team in front of it.
Alright, awesome.
Yes, we got it.
Signature.
Yes, there's one.
Maybe you're repelling.
Coach Cochran,
Yes, ma'am.
do you care if I miss your class on Thursday to go to college visit? Okay, thanks.
You're welcome.
All right.
As long as it's allowed.
You just take a second.
Yes. Who's proctoring the SAT? Like someone from my school or SAT? I meant like who's supervising?
Y does not matter. You know the Y. It's only the X. 2 is 7. So it would be figuring in the F and between. It's not a lot. It's one. That point. What is the range? Is just looking at Y.
You're mad.
So range is just a Y. The X doesn't really matter. So you're only looking at the values on the Y axis. So it's like 5.5. No, it's interesting. And then the lowest one is negative.
Okay, help me some of these.
So it's actually domain, so we're back to that.
6 and -6. See, my number 3 I would be like, okay, 0 and 1.
Hold on, it's actually range, we want all of them. So the highest point of the whole thing is the lowest point.
So 9,
9,
-4.
well, that's something like I've never heard of that. I wasn't taught how to do this in so I was taught these things like looking at it. Yeah, I'm passing. Like I know everything I know in New York except the one because I don't think graphs. I don't graph.
That's starting.
So these points again, so you're gonna want to have your long. They want you to list every point. So you just go pick 3 of them and then find the I think it's the first one. You can tell it. Okay.
Mine's 50. Because it wouldn't let me use my time.
So this one, you have to go down.
So what is this one?
I never used
This was algebra 1. This was like
it's been, I didn't have an algebra 1 teacher, because she was pregnant. We had a sub named Marianne.
What is the range? It ranges a lot, right?
yeah.
Okay, so
I put with our growth rules for your last 6
I'm not ready.
This is supposed to be in calculus.
Actually, it's still on.
We're just not starting out this week. We were which one I agree that I could. Like, oh, but I suck at geometry, I was better than you. I suck at geometry, I suck at math, but I'm amazing. I suck at algebra or at graphs and geometry. Geometry's not easy. Where you were, but I had 3 math teachers no matter 4 months. Geometry
I
is not.
took a 4 years worth of geometry.
Because Miss Holden, Miss Shen, to Miss Morgan.
That was us off the right with what we had to
Because
do.
they don't miss me, so we kind of.
We have Miss.
I had Miss Holden, then I had Miss Shen, and I had Miss Morgan.
Well, we had a classic.
And I only really had Miss Morgan for like 2 months because then we had COVID.
We had geometry in 8th grade, so I only had class like 6 or 7. So it was easy, like, it wasn't a class of like 20 what he's kind of talking. We were also in the very small room. We were in.
But now it's like,
You know Bruce Green's old office?
Okay.
Like,
Yes,
the
yes,
lower
yes,
school
yes, yes.
cafeteria?
Oh, yeah.
That's where we had class.
This is actually the direction of that. So here it's saying that F, but that's the line, is greater than
I never.
-2. It's smaller than 9.
So it,
You have to read them.
So
That's
is it-
9 out of 8.
so it not, this one? Oh, cause it's, it's blocked, okay, I was like.
It wasn't six, it was, give up the box six. But anything.
So there was volleyball season. Was there?
Oh, yeah.
I don't know, like, they're pointing in. Oh, it's
You said Marco?
okay, wait, now he's going to one Is it a function? It's asking you to process the vertical line. If it passes the vertical line, that's a function.
Freshman year.
You draw a straight line anywhere on the graph, and
No.
this crosses that vertical line twice, then it's not a function. You can only pass, and any vertical line you draw, can only pass it once, so it's a function. Yes. Okay. Wait, so, okay, you're saying it can only be one line. If you were to put a vertical line anywhere on the
October 17th.
this
Oh,
line would
What
only
about with
pass
playoffs?
that once and be a function.
Huh?
What about with
I
playoffs?
thought you meant I can only do one line.
Playoffs?
There's only one.
When's the last?
Cause you can draw a line, right? No, it has to stay vertical. If you were to draw a vertical line like that, it would be function, so I would say no. No. This is points, so this is
Well,
legendary.
Yeah, but it still can't be a function. It would just not be. It
I'm just gonna say prayer.
would not be continuous. It wouldn't be continuous as a function, but it would be a function.
Yeah, October 17th. That's the area time.
Yeah.
Are y'all gonna play after that?
No.
Okay, I mean, I thought it was a question that had 2 points, and I didn't.
October 17th.
So I said, I yelled at my.
Wow.
You're wrong. The
First
best
game
way
to
to
play
do it
is
is
November
tell
3rd.
us. Then my mom yelled at me for yelling
Yeah,
at
where's
me.
the only
My
one?
game is
The
November
only
3rd.
one that matters about the function
I'll
whether or
I'll
not
still play.
it has different points that overlap in exciting.
Unless like I get really aggressive and not lady like them.
That's what I was saying, I thought it was a boy sport.
Yeah. I'm so nice and not aggressive. They'll let me play.
But it's a boy sport. Just kidding. That's only a girl's game.
Well, it's not like what's happening usually with these freaking slides.
Yeah, it's pretty aggressive.
It's pretty aggressive.
Really fun.
It'll be fun. But you can't play soccer.
I don't know that.
Well, you can't play soccer if you're playing flag football.
Play soccer.
I like soccer.
friend to try to help me on ENS. I guarantee you ENS.
Well, I don't have one with like dating on, I like to dating.
Okay, it's going. Okay. Do I need photos in here and then? Okay. I don't care about the widgets. I think they're cute and I like them, but I can't get them to work on my phone for no reason. So that's what
I can put that in for like years, and I've never heard something.
I didn't even know they were apps until that big.
It is. I downloaded it. It's like casino lending. I'm like, don't know. You try to reset the phone.
No, it's just probably so excited, but still, they're not on that. I'm not, I said I'm not, but like, when my Wi-Fi comes on, I just turned it off. Oh, wait, yeah.
Right, so it's like not, it's not a big deal, but the problem is that's not what I'm doing now. I'm saying, so now I'm not sad. What? Oh, wait, you're not doing that? I don't like that.
And then you try to slide back and it won't let you.
I don't like that.
Yeah.
So, how do you give the kids to that? That's not. It downloaded. I said sorry. Oh, I thought you said huh? I thought you. So what do I do now? Yeah, that's fine. Okay. No, for now. Sorry.
There you go.
Okay, but does it show up? Because that's what it's been doing all. Like time is. Yeah, struggling, you guys. Okay. Outside, it's not there's glitter all over the floor out there. Like that's what it keeps doing. That's what I was saying. We can figure it out. But like it finally showed up after like a little bit on the other one. Like the big one I have on the other page, it finally showed up eventually. And I have like multiple photos so it'll go through. I mean, that could be a possibility. It's something that I love at Christmas. Mom said I can go deal with it or I can go on shirt. And I said, put it on. I'll take it back home.
Oh, shirts. I mean, yeah. I'm not sure they're gonna be done.
Well, that and
Because
that.
the was soft.
Well, yeah, but that and like.
Yeah, that's just the screen protector one. This one.
Oh, well, then you did it.
Yeah, I mean, I just gotta get my actual screen in case I want to use.
I think it's so weird. Thanks. Yeah, but Mom was like, well, we're gonna go on a trip. I was like, Mom, I'm going on a Christmas break. I don't need to take a Christmas trip. That I'm gonna get covered from. Thanks.
little bit harsher.
I mean, I'll keep playing with it, see if it'll finally pop up. But like that's, I was wondering if the time thing is messing with me. See, it says it's right on there, but if you go on the phone. I'll mess with it and see what happens. Thank you, though. I'm just gonna be messing with it all day until it works. Mia, is it not healthy to have a Christmas obsession way before December? What'd you just say? Is it not healthy to be ready for Christmas way before December? Diana thinks it's a little much. I don't. Mia does
I
not.
love Christmas.
Mia doesn't either. Mia started playing Christmas music.
Okay, Christmas music is different, and movies that's different, but like, setting up like everything.
Yeah, setting up everything is a totally different story.
Yeah.
Okay, well,
Music and movies, I'll watch in like July.
I watch
Yeah.
movies all year round. I feel like movies don't count anymore because all of them, I don't play music. Mia starts playing music in like October. Well, I'll be getting ready for Halloween, and Mia's like, Merry Christmas. But I do feel like once you hit October, it's like,
What time do we get out of here?
9:50. 10 minutes. Oh, I didn't realize it was already 9:40. Sorry. I was like, I feel like once you hit October.
SAT done?
Yeah.
Yeah.
Really?
Yeah. Once you hit like October, it's like,
Halloween,
Thanksgiving, Christmas, New Year, Halloween. Who wants Halloween?
make the highest score on the SAT?
Matthew,
Matthew who?
Spain. Him or Isabel.
Me this
I think
Saturday.
we'll do it. That's what I can do.
Spinny's a junior?
Yeah.
So Leo can make big grades?
Yeah, I think she'll make it.
What is it scored out of now?
1600. ACT only like, what, 36 or something?
This Saturday I'll get it.
You'll get a 1600?
I'll get 15.
Are you taking the ACT man in October?
I'm getting 15.
Like at the school?
What did you get?
Did she got 1440 or something?
What? Oh, you got really high.
That is really high. What did you get?
960.
Yeah, exactly.
I'm probably gonna wear a short on that.
I got 22 on the ACT.
Not better.
Well, actually, I'm wearing it.
It's good enough.
So comfy.
I quit learning in 5th grade.
Well, we all know why you're like the way you are then, I guess.
That's true. I got my master's degree.
What's up?
We were in here yesterday for Masters, and Coach Cochran left, and you were in there, and Mr. Sharp and he like, where are your teachers? And I was like, well, Coach Cochran had class, and we turned on Mass, like we were watching it, and she's like, well, where's Coach Anderson? I was like, I don't know, he's in. And she was like, well, where is he? I was like, I'm not in charge of him. And then we all got yelled at because we didn't have Mass on the big screen. I was like, I'm not gonna go on his computer. Like, I put it on my Chromebook.
I thought Miss Ott was watching it.
She was, so I don't know why she came in here
So why
anyways.
didn't you just tell
Well,
her?
somebody would've told me I'd have come and watched y'all.
Well, she got mad
I was
because
just working.
well, she got mad because I didn't put it on the big screen, and I was like, okay, but like I'm not gonna go on the teacher's computer. She's like, well, then how are you supposed to watch it? I said, we put it on the computer, and she got mad at me. And I was like, I don't know, she didn't tell me. Miss Ott told her she was watching it. She did like 3 times, and she's like, then how are you watching their class? Miss Ott was like, I'm watching both of them, and she was like, how?
What?
She's very extra about that stuff for no reason. She just wanted a reason to come in here. And then that stupid alarm went off at 10 o'clock. I was like, I've never been so annoyed in my whole life. It was like, ding, ding.
I was sitting in there grading stuff.
The alarm goes off, it goes off at like 10:27. Yeah, it went off at like 10.
Yeah, it's starting to die. It's not as loud as it was.
I know, it went off and everybody started looking, and I was just like, it's the clock from
What
like.
alarm is it?
No,
It
it's
used to
their,
be.
so like 10 years ago, they did like a senior prank and put a clock in the ceiling.
Yeah.
And they went to go get it, but they pushed it by accident and it went and now it's
There,
still off.
there's multiple in there.
Oh yeah, there's more than like one, but only one goes off.
Anymore. It used
Yeah,
to-
they used to all go off, but it used to be really loud and they're not as loud anymore. I'm surprised batteries lasted that long, to be honest. But they go off every day at 10, and we're usually not in here, but we were in here because of church, so it started to go off. That's all I know. I like. Bro, well, it was like 10 a.m. and it was going off and we were all.
My family is.
Huh?
I'm just travel fans.
That's like code for I don't work out.
Not seeing normal fans.
And then my mom's whole side of the family is coming in October. Well, the ones that don't already live here, so like her 2 nieces live here. And then, which are my cousins, and then that's it. Her sister
well, sister-in-law lives in New Mexico, and then what part of New Mexico? Albuquerque. She's a country director.
And then,
And so, and then Santa Fe.
yeah.
Have you been to Taos?
Where?
Taos.
Hells.
Taos.
Taos?
Taos.
I don't think so. What's there? Howell?
Pueblos.
I like that. Have you been to Blue Hole
Probably.
in New Mexico?
Where's the?
It's just like off that main interstate.
Well, then all five. Have you been to see Billy the Kid's Grave?
No.
Oh, you ain't living. So my house is gonna have 70 people, and I already said I'm not staying there. They're all gonna be there. I can't do it.
Where are you going?
My cousins, I'm not staying at my mom's and all of her. There's gonna be 5 of her brothers, all their kids, their wives, their girlfriends, or whoever they didn't see.
Oh.
My mom's brothers are not saints. None of them keep a girl longer than a couple of months.
They just have high standards.
Sure, we'll put it that way.
Now are you before? There you are. You're before, yeah. Real silent now.
Already telling y'all not to shine.
Give me your phone.
Mark, put this under there. The seat is already pushed in as usual. Now, Brian, go get it. Come on, run. Yeah, bro, you ain't taking that damage because I'm gonna start. When I get back, I'm gonna. Pull that some more. I got this. Pull that in. Hey, bro. All right, man. I'm real fast. Now you got away to there.
Hey, you capping on that now, Cleveland?
What? No, he hit 275 to come.
You swear to God.
Caleb? Yes.
Swear to God.
Yes. And I was like, hey, he hit 275. I was like, George.
George said he can power clean 255. Let's be for here. Sincere only got 245 today. And George knows dang well he don't fix 300.
Hey,
He's ready to do.
You waste
you can watch that.
Wait, so 220.
That part is boring. That's me watching that part.
I know you got some food in there.
There you go.
Wait, I know you got some snacks.
Huh?
I know you got some snacks.
It's in a car. I left my lunch in a car.
No. Wait, bro.
I'm not telling you. Oh, you getting checked out.
Wait, how can you do me like this, bro?
I don't want to be
At
at
the time that I need most. At the time that I need most.
Anyone got an iPhone charger? You got an iPhone charger? You got an iPhone charger?
No. Exclamation mark.
Hey, Quay.
Huh?
Big strong. Hey, Quay.
I know you got 200 today. He's still bitch.
Dad's bringing the whole group pizza today. Got about 3 of them.
Quick. He could have easily got 210. Oh, you. You made 200 look so easy.
Well, ain't a whole lot of y'all here.
There's a bunch of us. They're gone.
There's one more.
I thought we should have a chill day.
I'll take my lot.
Sophomore year? Your PSAT?
SAT. Karina can fight, bro. She got battle scars. A 90-pound warrior.
I'm not 90 pounds.
You're
I'm
like,
actually 106.
I won't.
Yeah.
Old body. I think it blows. Anyone got charger, bro?
Why did you take your sophomore year?
I'm taking again this year. Just to see.
This today.
I'm taking it later the year because all that.
Oh, you can't take your SAT because you're leg.
I'm gonna be twitching down. I'm gonna have to go in there with emotion. Oh, you suck, Karina.
What?
You're so bad.
All right, let's see. Canyon, Bonnie, Davis is online, Kaysen, Emerson.
You taking the SAT?
Is he taking the SAT?
I know.
He just wants to get out of school is what it is.
I'm just trying to get past. I'm trying to get like a 65.
Travis,
Here.
Frank,
200 points put your name.
Diana, Quiz,
Here.
Stephen,
Yep.
Elliot, Lopez,
SAT.
you taking the SAT?
Yes, you can.
You check my list.
Oh. How am I supposed to help you out? You need a charger or something?
Let's see, Quay. Ramos. Creation. She taking the SAT?
Yeah.
Alright.
Let's play.
You?
Karina's here.
We're taking the SAT. That's all I'm
Oh, yeah.
Then yes. Then yes, can you?
I ain't seen you at the school. I saw him on the road.
Alright, let's see.
No, I already said that you could.
I don't care. You call my name. Take the chance.
Last year, Anna. What about you, Anna? Right. You're like a boondock.
Dang, man.
She said it was like you from Blue
I'll fire you.
Look, you look at that.
You suck too.
Let's see, Gavin.
I think you're sleeping with.
I know you do.
Yeah, there he is. I missed him. Let's see, Juan Carlos is here. Davin up there. All right, cool.
Yes.
Can y'all do that?
What are we doing?
You bet.
That's so funny. What's up? Oh, I think
This is,
oh wait, what if it messes up my?
y'all move, y'all, everybody over here move over here. Everybody over there, move over there. Cosmic Journal, Journeys, Hubble, Universe in Motion.
Family vacation.
Not since Galileo invented the telescope over 400 years ago has our view of the universe been so transformed. In April 1990, astronauts stationed the Hubble Space Telescope in orbit above the blurring effects of Earth's atmosphere. It returned scenes of unprecedented beauty, as well as clear, sharp images of a dynamic, changing universe. Stars, planets, galaxies, each evolving in time from birth to dissipation and death. This portrait of a universe in motion is Hubble's enduring legacy. The Hubble Space Telescope is now regarded as one of the most revolutionary scientific instruments ever built. While not the only telescope launched into orbit, it has surely been the most versatile. Spacewalking astronauts returned 4 times to upgrade its instruments to newer and... As a result, Hubble has been able to probe the life cycle of stars. From their birth in nurseries of dust-laden clouds of gas, all the way to their final farewell as delicate nebulae slowly blown into space. Or known as titanic supernova explosions that outshine their host galaxies. Hubble has peered into the breeding grounds of new solar systems. Dusty disks around newborn stars that may condense into planets. And it has transported us into the billions of galaxies that spread out across the depths of time and space. One of the most photogenic galaxies is a grand spiral called M. Amateur astronomers have long known it as the Phantom Galaxy because of its low surface brightness. Hubble astronomers, on the other hand, saw spiral arms laced with delicate tendrils of dust silhouetted against bright ribbons of stars. These spiral arms are not like spokes on a wheel. They are density waves that move around the galaxy, compressing gas and stimulating the birth of vast waves of new stars. Using Hubble, astronomers are uncovering fascinating details within galaxies they once considered featureless and bland. NGC 1132 is an immense ball of stars some 320 million light years away. Astronomers have concluded that this giant is the product of a gravitational feeding frenzy. Hubble showed that its surroundings are dotted with dense clusters of stars. They are what's left of galaxies that were swallowed by 1132. How galaxies grow and evolve over time is an enduring mystery that Hubble astronomers have sought to unravel. The first galaxies are thought to have formed out of clumps of gas in the early universe. These proto-galaxies came together to form larger and larger galaxies. Such galactic mergers may play out over hundreds of millions of years. Hubble has shown that it is an elegant waltz of stars and gas, choreographed by gravity on a grand cosmic stage. As the galaxies pass each other, their gravity pulls stars and gas into the space between them, building vast, luminous bridges stretching tens of thousands of light years. As the galaxies fall together again, long streams of gas and dust, known as tidal tails, wrap around their disrupted shapes. As the galaxy cores approach each other, the gas and dust clouds that envelop them can be dramatically accelerated. This results in shock waves that ripple through interstellar clouds, setting off bursts of star formation that appear as brilliant blue knots. Gravity is not the only force that can tear a galaxy apart. Hubble spotted a spiral galaxy plowing through a cluster of galaxies. There, it has encountered a vast cloud of superheated gas. Drag from this cloud is stripping away gas from the galaxy, creating tattered threads of murky dust, as shown by the dark brown tangled region around the galaxy's center. When Hubble observations are combined with X-ray images, a bright extended fog can be seen enveloping the galaxy and streaming off into space. In the end, this encounter will leave the galaxy with very little gas and almost no chance of forming any new stars. galaxy collisions are not always destructive. Take the case of Centaurus A, 32 million light years from Earth. Shockwaves produced by a collision have sparked an intense round of star formation, as seen in the red patches visible here. The turmoil of the collision explains the warped shape of the galaxy's disk, as seen in this wide view from a ground-based telescope. There is something else about Centaurus A that stands out. Using radio and X-ray telescopes, astronomers have spotted powerful jets blasting out of its center, and broad plumes of matter racing far beyond the galaxy. Where is all that energy coming from? Answering that question has become a major focus of Hubble observations since the day it was launched. Astronomers have long noticed that the centers of large galaxies are unusually bright. They speculated that there must be some kind of massive object lurking there. Could these objects be dense collections of stars? Or are they a breed of supermassive black holes? Millions or even billions of times the mass of our Sun. Hubble's search for the answer began in the center of a giant nearby galaxy, M87. Astronomers saw that its color was not quite the same on both sides. One side was shifted towards blue, and the other towards red. A hint that it must be rotating very quickly. This is because the wavelength of light is changed by the motion of whatever is emitting it. This is also known as the Doppler effect. Think about how the pitch of a train. Similarly, if something in space is moving towards you, the wavelength of its light gets squashed, making it appear bluer. If the object is moving away, its light gets stretched, making it redder. By measuring how much the colors had shifted from one side of the disk to the other, astronomers were able to determine its speed of rotation. It turned out that this disk was spinning at a rate of hundreds of kilometers per second. Astronomers concluded that an object must be lurking in its center that's at least 4 billion times the mass of our Sun, a supermassive black hole. This was a key piece of evidence in the discovery that supermassive black holes occupy the centers of most, if not all, large galaxies, including our own Milky Way. Back in the early 20th century, the young astronomer Edwin Hubble joined a larger quest to understand the scales of time and distance that define our universe. To make his measurements, he observed stars in the nearby Andromeda Galaxy, just 2.4 million light years away. His namesake, the Hubble Space Telescope, has extended those measurements to the far limits of time and space. In its legendary deep field images, Hubble stared into seemingly blank regions of sky, revealing thousands of faint galaxies from the early days of the universe. These blotchy collections of stars are infant galaxies. Over the 10 billion years their light has traveled to reach us, some may have evolved into galaxies that resemble our own. With a supermassive black hole in its center, spiral arms, exploding stars, solar systems, planets, and perhaps even life. Hubble has shown that our Milky Way galaxy is a dynamic cosmic laboratory. Some of its most striking and beautiful images are giant structures known as nebulae. This one is nicknamed Horsehead, after its clear and curiously familiar shape. Rising from a sea of gas and dust, this so-called dark nebula is a cold, dusty cloud set against a background of glowing gas. Then there's the famed Eagle Nebula, nicknamed the Pillars of Creation. A group of hot young stars is scouring these luminous towers with fierce winds of energetic particles. Dense pockets of gas resist these winds. Within them are cocoons of gas and dust, where new stars are being born. You can see the same process underway in the Monkey Head Nebula, about 6,400 light years away in the constellation of Orion. The Monkey Head is a stellar nursery with all the ingredients needed for star formation. Its peaceful beauty masks the violent events within it. In places where stars are able to form at high rates, Hubble astronomers have zeroed in on the moment of birth. One team has been collecting high-resolution Hubble images of energetic jets of matter being shot from newborn stars. Unlike most astronomical phenomena, which can appear motionless over centuries of time, these jets visibly change on human timescales. Using Hubble, astronomers can see knots of gas brightening and dimming. This shows that these jets are not being launched in a steady stream. Rather, they are racing out sporadically in clumps. The irregular structure of these jets is likely caused by material that periodically falls onto an infant star. This image shows how violent the end stages of star formation can be. In the constellation of Cygnus, a few thousand light years away, lies a compact star-forming region called S106. A young star named S106IR is being born at the heart of the nebula. In the final stages of its formation, the star is ejecting material at high speed, disrupting surrounding clouds of gas and dust. 3D visualizations show the extent to which the star has carved its surroundings into a complex shape, including hollow cavities. At the outer edges of these cavities, the gas has been compressed into shock fronts. The material spewing off the star not only gives the cloud its hourglass shape, it is heating it up to temperatures of 10,000 degrees Celsius. The star's radiation excites the gas, making it glow like a fluorescent light bulb. A star is born when pressure and heat in its core cause hydrogen gas to undergo nuclear fusion. The heat generated by this process pushes outward, countering the inward pull of gravity. From the violence of their birth, most stars spend their lives shining in relative peace, gradually using up the hydrogen fuel that makes up their cores. Smaller, cooler stars are incredibly efficient. A red dwarf, with 10% the mass of our sun, can burn for 10 trillion years, almost 1,000 times the current age of the universe. By comparison, larger, hotter stars like our sun burn more quickly. At about 5 billion years old, our own sun has gone through half its expected lifespan. By observing stars similar to the sun, scientists now have a good idea of what will happen to our solar system in the distant future. The sun will grow steadily hotter, causing it to swell into a so-called red giant. When the sun does this, it will destroy the inner planets of the solar system. Next, the outer layers will puff out, forming a dense cloud of gas and dust that will obscure the visible light from the star. In this stage, it forms a protoplanetary nebula. Only dim infrared emissions from the dust cloud and reflecting starlight let astronomers see anything at all. Hubble images of this stage show a wide variety of shapes, hinting at the complex dynamics at work inside. The spiral structure of this nebula is particularly unusual and is likely due to a second orbiting star that is producing swirling patterns in the gas and dust. Over a period of a few thousand years, radiation from this hot remains of the star excites the gas in the nebula, causing it to glow. The once faint nebula now becomes a bright and mysterious cloud called a planetary nebula. This type of nebula populates our galaxy with luminous shapes that draw the gaze of many a skywatcher. Eventually, planetary nebulae fade to nothing as their gas and dust diffuse into space. All that remains is the tiny white dwarf, a form that our sun will take billions of years from now. Planetary nebulae are more than just beautiful shapes that grace our galactic skies. They show important stages in the life cycle of stars and how they interact with and even shape their surroundings. Hubble has given astronomers the sharpest views yet of these ghostly dynamic structures. Take the Ring Nebula, just over 2,000 light-years away from Earth. From Earth's perspective, it looks like a simple elliptical body with a fuzzy boundary. But Hubble observations show that the nebula is shaped more like a distorted donut. The donut hole may look empty, but it is full of lower density gas that stretches toward and away from us, creating a shape a little like a rugby ball that's been slotted into the donut's hole. The space surrounding the nebula is turbulent and full of knotty structures that formed long ago. If we were able to rotate the Ring Nebula by 90 degrees and view it side on, it would look more like the nebula. In the act of dying, sun-like stars cast most of their mass out into the galactic wings. In time, the atoms in our own sun may well be swept up into new suns, new solar systems. In the cycles of star birth and star death, The galaxy is dominated by a rare and extremely violent green. Stars 10 times the mass of our sun, and even larger, burn hot and fast. Intense temperatures and pressure ignite nuclear fusion reactions in their cores. Hydrogen gas turns to helium, oxygen, carbon, calcium, silicon, all the way to iron. The upward pressure from heat radiating from the star's core is no longer enough to hold it up under the crushing weight of these elements. Gravity wins the battle, and the star's core collapses inward. That produces a shock wave that races up through the star's volume and obliterates it. Of the 200 million odd stars in our galaxy, one goes supernova about every century or so. The last one to be seen in the Milky Way was observed by the astronomer Johannes Kepler in 1604, just 5 years before the invention of the telescope. The most famous supernova in recent years appeared in 1987 in the Large Magellanic Cloud, a dwarf galaxy just above the plane of the Milky Way. It was so bright, it was visible to the naked eye. Launched 3 years later, Hubble has been tracking the evolving spectacle for over a quarter of a century. Astronomers have marveled at the complexity of the explosion, including the patterns etched by its expanding shockwave. In time, the dusty clouds it leaves behind can last for millennia. Their effect on the surrounding interstellar gas lasts even longer. Although no supernova in our galaxy has ever been observed with a telescope, plenty of supernova remnants have been. Hubble's sharp images of their complex structures help explain the sequence of events, as well as the profound impact these explosions have on the galaxy. Take the Crab supernova, one of the most interesting and most studied objects in all of astronomy. Japanese and Chinese astronomers witnessed the explosion in the year 1054. The filaments shown in these images are the tattered remains of the star, consisting mostly of hydrogen. The collapsed core of the star, embedded in the center, is barely visible in this Hubble image. Yet you can see its effects. The bluish glow comes from electrons whirling at nearly the speed of light around magnetic field lines that extend from the star's collapsed core. Astronomers have been poring over the nebula itself, still growing at a rate of 1,000 kilometers a second. What they've found is that the filaments of matter that roared out of the blast contain large volumes of dust, an array of mostly carbon or silicate compounds that absorb visible light. These solid particles are crucial for the formation of solar systems. Within the Crab Nebula, there is enough dust to make 30 to 40,000 Earths. Galaxies all around the universe bear witness to the dusty legacy of countless supernovae. The bright central region of the famous Pinwheel Galaxy, for example, is surrounded by dark, dusty lanes. In spiral galaxies, hot winds from exploding stars have helped push those clouds toward the periphery, as well as above and below their flat disks. You can see evidence of this in our view of the Milky Way galaxy. Dark dust lanes and ominous clouds dominate our view into the disk, while tendrils of dust reach far above it. Some dust clouds are destined to light up with new stars, as you can see in one of the Milky Way's small companion galaxies, the Large Magellanic Cloud. Its most dramatic feature is the Tarantula Nebula, a bright region of glowing gas and energetic star formation. The tarantula, shown in these Hubble images, glows brightly because hydrogen gas within it is being excited by ultraviolet radiation from newborn stars. In a wider view, the luminous Tarantula Nebula stands out from its host galaxy. It is the brightest known star-forming region in the local universe, and one of the most attractive spots in the night sky. Thanks to Hubble, there is a place within our own galaxy where you can see not only stars, but solar systems being born. In the constellation of Orion the Hunter, just under the three stars that make up its belt, is the majestic Orion Nebula. It draws our attention for its beauty and mystery. Ancient civilizations saw meaning as well, including the Maya in what is now southern Mexico and northern Central America. In their story of creation, three of the brightest stars in the Orion constellation represented a hearth. The nebula was the fire that warms it. At 1,500 light-years distance, it's one of the best-known examples of a star-forming nebula. A swirling cloud of gas and dust, where stars begin their journey of light. Within it, Hubble astronomers discovered isolated pockets of gas called proplyns. These are protoplanetary disks that form around newborn stars, in spinning up to be planetary systems in the making. The brightest star, the Trapezium star cluster, affects the nearby disks by heating up the gas within them, causing them to shine brightly. The excited material produces many glowing cusps that face the bright star. Other interesting features enhance the look of these captivating objects, including jets and dramatic shock waves. They are formed when the stellar wind from the nearby massive star meets gas in the nebula. The interaction produces shapes like boomerangs or arrows. In one case, the shockwave makes the proplyn look like a space jellyfish. The powerful radiation that allows us to see these shapes also threatens their existence. Once heated up, the disks are more likely to dissipate and dissolve, destroying their potential to spawn planets. Some of the bright proplyns are doomed to be torn apart. The dimmer ones are the most likely to survive. Among those that do produce solar systems, Hubble has been documenting a wide diversity of planets. One of them, known as HD 189733b, is a huge gas giant similar to Jupiter. It lies extremely close to its star, as shown in this animation. Proximity to the star makes its climate exceptionally hot, with temperatures exceeding 1000 degrees Celsius. A team of scientists used Hubble to observe it as it passed in front of its parent star. While backlit in this way, allowing astronomers to decode what is happening on scales far too small to image directly. They expected to confirm that the upper layers of the planet's atmosphere are boiling off under the intense starlight. Hubble's first observations showed no trace of this. Just before it could take a second look, the Swift satellite detected a huge flare coming from the surface of the star with powerful atmosphere-flying X-rays. When the planet slid into view a few hours later, the changes were startling. Where astronomers had seen a slumbering planet before, now a plume of gas, the planet was losing at least 1,000 tons of gas from its atmosphere every second. There's no life on a planet that orbits so close to its parent star. Such planets, however, are allowing Hubble astronomers to open their search for Earth-like planets further out. When the planet moves between the star and Earth, Hubble has been able to capture a small fraction of starlight passing through the planet's atmosphere. Astronomers are looking for a hydrogen-carbon compound called methane. On Earth, it's produced by a combination of natural and man-made sources, including fossil fuel production and livestock. On this hot Jupiter, methane is probably produced by a complex chemical process in its atmosphere. Astronomers plan to use data to identify prebiotic molecules in the atmospheres of planets in the habitable zones around other stars, where more moderate temperatures will allow liquid water to flow. The new measurements are an important step toward the ultimate goal of identifying the conditions, such as temperature, pressure, winds, clouds, and chemistry, on planets where life could exist. Astronomers have detected a wide range of planets around other stars by looking for clues, like the wobbling motion of a star as a planet. Hubble was able to capture, for the first time, a direct image of a planet. Visible from the southern hemisphere, Fomalhaut, it is 15 times brighter than the sun and much hotter. This star is blazing through its hydrogen fuel supply at such a furious rate that it will burn out in only 1 billion years, 10% of the lifespan of our star. Its most interesting feature may be a large disk of dust and gas that surrounds it. This strange ring is not exactly centered on the star. Astronomers suspect that the gravity of another body, perhaps a planet, is pulling it out of shape. The suspected planet is a dim speck. To see it, astronomers used an instrument called a coronagraph to block the star's light. Then they gathered a host of clues to find out what it's like. For one, the shape of the disk hints that the planet is at most 3 times the mass of Jupiter. For another, the planet is much ring system that reflects starlight in all directions. One day, the material in these rings may even coalesce to form moons. is part of a larger quest to discover and understand solar systems, including our own. Have used Hubble to track the changing climate of cloudy Venus. Dust storms that sweep across the planet Mars. The aftermath of Comet Shoemaker-Levy's collision with Jupiter. Saturn, Uranus's rings, and Neptune's intense, turbulent atmosphere. In our solar system, few Hubble images compare to its views of Saturn and the fluttering aurorae that light up its poles. Scientists created a movie from data collected over several days during January and March 2009, when the rings appeared edge-on and both poles were visible to us. All parts of the solar system. When this electrically charged stream gets close to a planet with a magnetic field, like Saturn or the Earth, the field traps these particles. The magnetic field is stronger at the poles, so the particles tend to concentrate there, where they interact with atoms in the upper layers of the atmosphere. That's what creates the familiar nighttime glow we know as the northern and southern lights. Saturn's auroras are not only charming features, but they might teach us something about our own planet and its magnetic field. Beyond Saturn's dancing lights, or the sudden explosion of a star, the universe appears unmoving against the ponderous march of cosmic time. Among its greatest achievements, the Hubble Space Telescope has been able to track the large-scale motions of the universe. Take an event close to home. Astronomers have long known that the Andromeda Galaxy, currently 2.5 million light-years away, is moving toward our Milky Way. A team of astronomers used the Hubble Space Telescope to find out how fast the two galaxies are moving, and whether there will be a head-on collision. They tracked the motion of stars in Andromeda, then projected their movement into the future. Based on these findings, they showed the course of events over the next 8 billion years as the galaxies move closer, then collide, and gradually merge into a new, larger galaxy. If you could wait a few billion years, our night sky would change dramatically. As Andromeda approaches, it will loom large in the sky. Later, when the galaxies begin to merge, they will twist and distort under the pull of their mutual gravity. In time, the new combined galaxy will become an immense ball of stars, what's known as an elliptical galaxy. Even though these two galaxies each have hundreds of billions of stars in them, the stars are all relatively far apart. The chance of any two colliding is extremely small. Our Sun, born in the Milky Way almost 5 billion years ago, will follow a new path as it orbits a whole new galaxy. In the universe according to Hubble, galaxies all across the cosmos are circling each other, merging, and moving into ever larger and denser groupings. Using Hubble to survey patterns of galaxies, scientists have been able to map a mysterious substance that envelops galaxies and clusters of galaxies. This so-called dark matter adds to the gravity of these structures and has been driving their collapse over time. Because of the arrangement of galaxies, astronomers have long known that dark matter stretches out across the cosmos in a vast web-like structure. Actually observing this web has been difficult. Now, a team of scientists has used Hubble to make detailed observations of a dark matter filament, measuring its length, shape, and density. Theories say galaxy clusters form where filaments of the cosmic web meet, so the team focused Hubble on one such cluster with a stream of galaxies moving into it along several filaments. The astronomers used data from several ground telescopes to measure distances to the galaxies within the filaments mapped by Hubble, and to trace their motions.
Have a good day. I'm having trouble. Do anything stupid.
Your face is rubbing on. One.
Oh my god.
What a big class.
Hey, John, at least Fox here. Fox here. My Spock? Yeah. My second period was me, Spock, and all.
Jonathan, you're not taking the SAT?
No! I kept wanting to take, I heard about it like a week ago, and then I was like, I should go ask them, sign up for it. And then I didn't. And then they mentioned it 2 days ago, and I'm like, I forgot to sign up for it. It's too late now. Because I didn't, and also the thing is, I have an IEP, so I don't take it with everyone else.
Claire, was your ear like huge?
Oh, did Dad tell you?
Yeah.
So.
Why did you super do your ear and your ear?
So literally, your dad was like our last resort. I was like, wait, Jackson's dad might have some wire cutters and pliers in his truck.
See, this
Your
is
dad,
why
we
you
were
like
right
you
about
just
to
sitting
start
where you're at.
starter, so he
You're
ran
not even.
and they got
it's
these
finishing.
huge
Yeah, I know,
wrenches
but
and
I'm
literally
doing it
like put it on my earring and ripped it out.
Oh, why? Okay, but why do you choose those?
Because it's the new
But you had to rewrite
it. And it was acrylic like nail glue, so I didn't think it would stick that much. But I couldn't break it. And now it's super small. It was so big last
Why
night.
not just put it in? Like, why do you have to sit
I've rewritten it.
Because it was like there was a class. And it's a class.
You lost the class?
You have to lose the class.
Shut up, Donovan. You want to have a conversation.
What conversation?
So the class, it like clicked like.
Oh, a
this.
class. With a
But this part where it clicked into was broken. So I just super glued this part together. While I was in.
Did you use both earrings or just that one?
No, just that one.
You tried to hurt?
Yeah, it
Why did-
hurt.
why
My
did it
ears
swell up?
throbbing.
Why did it swell?
Because we were all trying to pull it and yank it out. And
That was a
like
terrific idea.
Mallory took a pair of scissors and tried to cut it out of my ear.
Let me try cutting my earlobe. That sounds like a great. That's the first thing I come to every time I do something.
Dude, you don't understand.
If I get my hairband stuck, let me cut off my head. You know,
If we
my hair gets tangled catching my hairband. I'm gonna just cut off my neck. This is a great way of
it
doing
was
it.
so bad because our service team was really what? Well, the problem was that they only had one good hitter, but back row couldn't pick up any
I thought
more
they're full like
hits.
one game with this.
In our scheme that we create,
They're
however
Rivero
we
and
create it,
Genevieve,
we use to
they're
create a
outside
high
there.
pressure system and then fire something.
Because they're middle
What
weight.
I think I follow on Instagram. Genevieve Richards.
That's what I want to
We should
happen.
put it in.
I don't know, I don't care. But what do you mean?
I mean, I guess it's technically
But
pressure.
servicing was awful.
I thought you tore your leg.
Everyone just kept getting hit with more.
The thing is, I get to a point. Well, also, is that the labrum is only the labrum just holds in the shoulder. So if it doesn't come out of the socket,
All I need to American go.
which this is not out of the socket.
1607.
If I do this, that is out of the socket. If I lift something like this, I can't do lift anything heavy. I could lift that like that.
Okay.
I think I tore my leg.
All right.
About it.
You can still.
Yeah,
It's not really that bad.
no, but mine was completely traumatic tear.
On your dad surgery, because I also tore my left leg.
Mine was a complete traumatic tear. That's the reason. This one, I have some tear in, I can tell, but based upon the comparison, but it's not enough to do anything about it. If it now if it got worse, then yeah. If it kept getting worse, but it has to get just like a tiny bit. But it's nothing compared to this one.
John, go grab that empty bucket up there.
You mean the clear this one?
Yep.
All my abs to be like.
How do you do that? How do you change your app, what your app image is? How do you do that?
It's
I really want to see
you
this.
have to do it through shortcut.
Wait, do you have to get? Do you have to update it?
Yes.
The thing
What's
is,
your Instagram name? Mine's Mahmoud.
Alright, let's take apart the sewing machine.
wait, where's the sewing? Are we actually taking apart the sewing machine?
A motor.
Stop, did you post on Instagram?
All right. Let's see what we got here.
I don't know if I should follow you back.
All right. We have a Sears Kenmore motor made in Japan. This came out of a sewing machine that was from the 60s.
I have one.
It has run. This was my mom's, and it has run until 2020, so it is 50-something years old. This motor ran for 50 years.
I bet it's American made.
Is the economically the best place for construction?
children.
Literally,
Okay, but China also makes crap, so.
it makes crap because that's how much they put into it. All iPhones are made in Japan too. I mean, are made in China. You know that, right?
Yeah, but crap.
You have an iPhone.
I know, it's crap. I just have it.
The point is, it's economically the most efficient way because it's a lot cheaper to ship it all there and then ship it to the world than it is to ship it to the world and then ship it out.
Slave labor's cheap.
That too. Actually, they did that. They actually calculated, and even if we could beat their wages, it's still cheaper to do it there because of their geographical location.
Do you know that they have suicide nets in Apple sweatshops in China?
Apples?
Yeah.
Yeah,
It's like
like-
they're pretty much slaves, so they'll have nets in the buildings so they don't jump out the windows and kill them.
Well, they're slaves to money, which everyone is.
No, they're slaves.
No, they're
communists.
everybody's
Well, that too, but essentially that either they have money and to buy food so they live, or
Two
they don't
ways
have
to
money.
make a slave.
You force them to do what you want them to do via government rule, or you
No.
physically force them to.
You can pay a man, you can work a man without paying him, pay a man without working him. You do whatever you want. Either way.
So, like how, like a bodyguard would be a slave?
No.
No.
They just stand there.
Well, no. Their
No,
job
'cause
is
you're doing a job.
if they don't have to do anything at that certain moment.
All right.
So
Let's
you're
not
saying-
lose anything.
So you're saying if you pay someone off?
Because the goal here is to make this thing work again.
Yes, I was on the defense.
I can't tell you how many times.
I know it's burned up. Fire was seen coming out of it by my mom.
Oh.
Maybe some WD-40 it looked like.
We don't
Let's get
wanna,
some WD-40.
we
WD-40.
don't wanna do anything to it till we,
No, I'm like trying to slick it up. That I'm trying to like say let's slick it up some.
what we're dealing with.
I saw it on the list.
These all the.
Do you know it?
So,
You should keep it like that. It's cute.
Wait, so y'all talking?
obviously,
Let's get in there.
It looks.
let's get some magnifying.
It looks charred. This looks. It's oily and.
Told you it's burned.
I think you just need to replace the whole thing.
You know what the next step is?
I think you actually just need a new motor.
Look at that.
Make sure you
Can we
bring
get
it
Alex
over.
down?
Look at it. It's
So you
like
and
all
Alex-
the way burn.
all the way.
do a double date with John and Lucy.
Some of these are.
Yeah, that would be
Alright, you and Addie?
Actually, I'm gonna go hang out with Lucy and Molly.
This
Because
seems
I
fine.
have no idea.
That's literally
I have a
just
bonfire burn all of Ben.
the holding piece is all that's intact.
This seems like it could be damaged, but.
Oh yeah, you know the entire motor. Yeah, that
That's
seems a
what
little
we always
damaged.
talk about. We're like, oh my god, what if Ben today isn't Bradley and Austin?
I'm sorry, I
What
heard
if
that.
everyone's dating this year?
You know Alex is used to doing sarcasm.
Yeah, I heard
I
that
don't
too.
care about. That's weird. Why would you tell me?
Good
that?
answer.
That's
I wanna go to
disgusting.
That's a good answer.
Like, do you think that we could prevent something that was like heartbreaking today that just to let us go to
I really
Burger
don't care. That's no.
Like, just we walk up to
That's
Burger King and just
disgusting.
get
Like,
good
that's
food.
bad. I don't want
You think we could
Maybe
get
14
Miss
would be
Mendez? Okay, we're going to our car
You're
for
gonna make
20
me wanna
minutes.
turn
We'll be
him
back in
down.
just a
Keep
second.
going
So
up.
are you?
No, I think that's like 30 minutes.
Why would it? Okay, we'll be back in 30 minutes. I have something in my car. Yeah, and I'm gonna walk
Burger
in.
King is just
Hey,
up
did
the
you,
street.
like-
Yeah, I know. I
Wait,
thought-
we go to Burger King?
Jonathan, who did you hit?
Jonathan, we go to Burger
Who
King?
did you hit with your cards?
I didn't hit
Who
anyone.
hit you?
Oh, my mom backed into me. My
Alright.
dad hit it 2 deers.
Oh.
Oh, and then
Today?
no.
Oh.
Let's see
I
what we
only
got
hit
here.
One person, and that was in the pitch black.
You hit a person?
No, oh no, the car. In pitch black, I was backing up. The entire back window was fogged up. Everything was fogged up. Pitch black. I backed into one car.
Jonathan.
No damage.
Jonathan, do you remember when I was in your 4th grade class? With Miss Williams?
I don't remember a lot of things, but I do know you were. And I went to elementary. I don't remember specifically.
Eagle Ridge?
Yeah, I know. No, I know that, but I don't. I can't remember a specific event. I know you were
This
there.
is
I know
our
you were in class. I
magnet.
don't.
And
That is
So there's a magnet?
magnets. They have magnets and motors. So that one, not charted.
Listen, I have no idea how motors work. So I'm looking.
Well, also it depends on type of motor, I guess. Could we make a combustion? Instead, turn into a combustion.
I started taking part
Yeah, I like that idea. She has to do it.
And then is your car dangerous?
Let's change parts in my
Oh, yes. But
You get so you see my point though. And also, if you stab your phone, it has a chance of exploding because it's a lithium battery. So
yeah, that you.
and you
we
put
all
that
laughed.
right next
We
to your
thought it
head.
was so
So the
funny.
copper's
That was like-
obviously burned.
This copper looks a little. Oh no, is that burn or? Yeah, no.
Dude, my mom said I
That's
could.
how lucky you are.
It's, some of this looks like
I'm
grease.
reading your phone. My birthday was like 3 weeks ago.
Well, it
They haven't got me.
probably is, but that's probably
I
what
just
caused
tried
the
that.
fire.
That reminds me of this.
Can't lose
I've
any
never
of
been.
these.
It's like a.
That's just looks. That's like you want like for the sake of.
It's like what you and Caroline
So
are.
probably,
I mean, y'all look
how
alike,
can
but
we
like I
get
just
that off?
can't. I can see it in the personality, but like I just don't.
Where did
feel
you go
like
to
you're-
school?
Oh yeah, because it told him and dad, and then probably just slide through.
So where
It's
is she?
like great.
Oh, nature.
She plays
You're
on
just
game.
eating.
Oh,
Oh, I think. Oh,
is she good at one?
Does it? Ooh, these just open up and you can take these copper wires off.
That was the worst wink ever.
Who winked?
Claire. But she winked like this.
Add it to the list of things that are broken about me.
Earlobe.
It's not broken, it's just.
Wait, which one was it?
Okay, ready?
It was the one with.
Squeeze this one.
Oh,
Ready? Now
let me squeeze the
gently,
earlobe. Just
gently
squeeze the
touch
earlobe.
this
Squeeze
one.
the
Or
earlobe.
I will scream, okay? Do you feel the difference?
Yeah, it's a little bit.
Oh yes, this is a quality earlobe. This is a non-quality earlobe. I can tell by the way it squeezes.
Oh my god, I will scream.
No.
Ah yes, this earlobe is very right.
Do you understand, like?
Are you able to like, cause these panels, which I assume to be copper, the whole thing's copper.
I'm not that anymore. The wiring is copper, and you can see some of it has actually come loose on this one.
That is that one? Is that fit fine, or because these things actually just open up a little bit, and you can pull those off? I like this.
We're exploring right now. We're just observing.
All right.
Come here.
I don't want to do this. Come here. I don't want to.
Come here.
All right.
So what is this?
Well, that was what
Alright, this is part of the magnet.
I don't know what that is.
I believe it's
I don't like that.
or they might be copper.
I know you like that. I really don't trust you. That smells really bad, so I'm not going to eat it. It smells bad. It smells bad. I think I know those are. I just don't know what they're called. It smells real. I forget what are those called. I forget what they smell like green. Yeah. What are they called? What he's eating. They smell
Everybody,
bad.
Jackson.
They're like.
I have no lunch.
Jackson, look at the camera. Jackson.
You have two right there.
Were you talking about edamame?
Darling, just eat one.
Take a picture.
Oh, on that side, the big black one.
Just press the button.
Jonathan.
And then there's two on the end cap, it looks like, that aren't black, but.
No, I got those off.
Oh, okay.
Just eat one.
This smells so bad, I don't think I want my breath
They
smelling
smell
like that.
like
Because I have a mask on, and I think and I don't want to smell that for the rest of the
like
nothing.
I have a better nose than you.
Oh, it's magnetic. Do you say you have a better nose than him?
Yeah.
I also have better ears and, well, I mean, not necessarily the things themselves, the details of the car.
Huh?
What are
Sidewalk's done?
Yeah.
Yeah, that's how motors work.
Well, not. Electric motors specifically, because electric motors, when you turn on a magnet, it pulls it a certain way, and then it turns it when it pulls it.
So this is like the diagram that was on the board a couple days back?
Yeah. One of them. But then the combustion engines work by powering pistons, which it pushes it down and then goes up, and pushes it down and goes up.
I understand the piston.
So different, but electric motors will always use magnets, and also they also can use renewable.
Once a dead period.
I'm not going to eat that. That smells so bad. What are these panels? Those are the magnets.
Magnetic.
It smells a little bit, but not bad.
Magnetic.
Exactly. Jonathan's just.
Leave that stuff alone.
Oh, those are rusted, so that wouldn't have done anything anyway.
Is it still magnetic or no?
Not as much. Or actually, it might not need to be as
I
much.
meant at all.
Yeah,
It seems a little bit. There's a little bit of pull.
I just wanted to see how much damage was done to it, because if the fire was sustained for long enough, it wouldn't be magnetic at all.
But question is, was it ever that powerful, or is that actually how powerful it's supposed to be?
I'm not sure that it was ever all of that.
So that could be how powerful it is
I
normally.
mean, it was a motor for a sponge.
Right.
So
That's
how
why
much power do you need?
Exactly. That's why I'm like, And
These things spin fast.
I'm not
now.
gonna eat that. I'm not gonna eat that.
Why not?
Because
You
it's
gotta
so
say a
terrible.
sewing machine. I mean, it's got some power.
I mean,
Now it does, you know.
it has power, but it's pushing barely anything.
Yeah, it's not pushing much.
Now, if it was pushing something heavy at that, then yeah, that would be.
Yeah, sewing machines good.
But they're literally pushing a 0.5 ounce pen up and down.
Do you guys have any standing up?
That, but because it's pointed, there's a very minimal resistance because it's a very sharp point. A spear, it's a lot easier to stab someone with a spear than a trident because there's less surface because it's you know, I'm not stabbing you with a
Boy,
blunt.
that tolerances on that thing are tight.
Do you think WD?
Nobody has your lock.
I don't
I
want
like
to
that.
spray anything on it. Don't want to put anything on it right now.
That's my favorite.
I mean, it got pretty hot.
Do you think we could get pliers? We could share pliers. So like one of us puts on one end, one of us puts on the other. Pulls.
Don't want anything dented or scratched.
At least maybe that one end, not the casing. Because that end doesn't. You got these, which
It's still going.
No, my dad meant
well, I mean, if it goes this end doesn't look like it did that could dent, but I don't think the main what's being encased will dent.
Oh, you should have just like, no, we're not going to.
And see the copper wire.
Yeah.
See where the copper wire down in there is.
Dude,
Ground into that.
I was driving. No, I was driving
See,
me and
right.
Alex, and
Dude,
Lucy
y'all know-
literally swerved out in front of us because she was on her phone driving, and she almost hit us.
Y'all ever see? Do you ever see the dude on Page?
And then
Is that the guy that's
it'll
like,
work.
Is that working?
The Beast of Carnage.
Or better out top?
I see it.
Show it down
Have you
there.
ever seen the
Show it down there.
He's so corny.
No.
Yeah, have you seen his highlights? Beast.
That's where the copper comes
Training on
from.
all he does is like run up after the guy, never get too near. Have you seen him when we got
This
blue up?
spins inside.
And the copper, as the electricity faults go, it goes through the copper, it pulls from there.
Guys, I'm gonna make all my apps white.
Also, the ones that I really there isn't a rail gun, actually a coil gun is better. Is actually what I was thinking of when I was thinking of a rail gun, because a coil gun works and with it pulls it to a point, but then if it keeps.
That creates
What are those?
the tolerance is probably for cooling.
How could it? But it's like solid, so it's not going to the rest of it. It's just stopping.
It's just keeping the air moving inside of it.
Okay, because it has the ventilator.
It's dented on both ends.
It's so funny, dude.
That's where
It's so bad.
it's an electric motor, so we've got electricity coming into it. It spins to create kinetic energy.
I hate it when they
Here.
Why are you eating your lunch
like
right
It's
now?
got to spin really, really fast.
like similar to new cars. They don't make them to be worked on. They design them to
Well,
Cheap.
this motor has worked for over 50 years.
yeah. But with
I mean, it's
UJ football.
That's a lot.
pretty impressive.
Yeah.
Japan makes
yes, anime
Who?
quality anime.
When they all get to hear me.
Who?
Yeah.
Got red.
Nissans.
I was like, y'all should just date her. Because we were talking about it and maybe not. No.
Where's Jeremy? Esta es España.
¿Dónde está la biblioteca?
I know.
No.
Ginny comprend la biblioteca.
Ben has to go see Molly today.
But it smells terrible. I smell it on his breath.
No, we're talking about something different. I don't know. If you need space, library is a great form.
I don't know where the library is.
You know, like,
Ah.
she's not afraid to hurt people.
I could
let
probably
people
score
down,
eventually.
she's not afraid to-
Oh, actually, yeah. It was terrible for me because
And then,
apparently
yeah, and
I was
then-
told this, but I'm dyslexic, and then I heard I was told French is the hardest.
Where is
They're just not
she?
even
Obviously.
Speaking language is hard to learn because I'm dyslexic. But
That's like,
There
that's
would
how
have to
bad
be
it
an
is.
electrical
Just like broader.
Morgan forces ego.
Where?
Actually,
And
that
No, you don't have like
Here?
well, that was just a black. That black flag looked more like a ground the way it was. Didn't look like it was. Oh yeah, because you had those sticking out either end, so I think that probably was those the rod running through it. Probably.
How long have you been here? It is.
Third.
Wait, no, because then it wouldn't connect to the copper. What about those little holes on either end? Do you have a picture of how it was connected?
I should be. My parents keep going.
Actually, that's where these came.
Yeah, but those don't look like any, like, I don't think this has any electricity going. It's, yeah, it's plastic. Yeah.
That just held the
Ooh, there,
mount
here, and here, and there. Those three.
It's not Spanish.
That's the only thing that looks like an actual, like, any connection. That makes sense.
Yo puedo hablar en portugués. No, they're not even close.
Here?
Right at the bottom. Those three.
Now.
There are some similarities, but not even close.
Maybe this, because that's the only other thing I see on, because it sticks out, like it's actually meant to come in contact.
Italian and Spanish are closer.
Yeah,
Well, they're all romantic languages. They're all in the romantic group.
Who's antisocial?
This is the first
What is romantic? What are the?
Literally, you didn't come to like anything we did over the summer.
Like Germanic also uses the same alphabet, right?
Germanic.
Yeah, it is Germanic languages. There's romantic, Germanic, and then there's the other ones.
Very introverted.
There's Germanic.
That's what I meant. That's what I
There's
meant.
Germanic, romantic.
And what's the other one? It's the one that's Russian, Greek, those roots.
Slavic.
Slavic. Those are, that includes
You
Greek,
didn't go to
right?
freshman homecoming?
No. Greek is unique.
What about, and Latin is a romantic. What are,
Latin isn't.
Basis?
No, Latin isn't romantic.
yeah, it is. It uses the same
You can
alphabet.
have a Latin root without being romantic.
No, but
No,
Latin
it's
is the
about
basic, is a
language,
romantic
it's about
language.
romance.
There's a language
I should have a
in
movie now.
Northern Ireland
Wait.
that is Slavic, but it's a
Wait, is
it is based on Latin.
Hebrew and Arabic,
About boys?
those are
But
different.
they've been
What
like
are
begging
those?
her to date.
Aramaic.
Oh yeah, they are. That's what they are. Aramaic language. That's right. And then, what are other Germanic languages? Germanic.
I was.
She's like,
What are other Germanic languages? I can't think of any besides German.
Norse.
Okay.
Swedish.
All the northern.
who would you turn down?
That's.
English.
Oh, like hanging out?
Well, actually, English is more.
English is romantic. Yeah, English is romantic.
No, it's not.
Yes, it is.
No,
It's a mix between German and Germanic.
Huh?
English is Germanic language.
I swear, I thought it was more. I thought
If you want to get
English
into,
and German. I thought it was romantic and German.
if you want to get into technicalities,
They have all crossed over so much.
exactly. If you want to get into technicalities, it is technically both Slavic and Germanic, but it is more Germanic than
You're
Slavic.
saying it's 0% romantic?
That's a good thing.
No language is 0% anything. They're classified based off of like what their roots are exactly.
All of middle school and then.
I find it funny that like
You just
Hebrew,
messed up.
like Aramaic languages really have a crossover like anywhere besides themselves.
That's not true.
I mean, relatively.
And me.
Or like,
Oh, was that the same night?
like name a country that we have. Yeah. What do they say?
So it's not.
English and Arabic.
Yeah, Arabic. That's an Aramaic language.
So they crossed
I want to know where the power goes in. Because the whole thing, this is not a generator. This does not generate electricity. But if we reversed the poles, we could make it a generator.
Actually, yeah. Look, there's that copper inlet there.
Oh, that's for this.
That's what I. Yeah, but what does it have? No hole through it? No, it doesn't.
It could be here.
That's one thing.
Because maybe I'm missing.
It could just like
part down
slide
here, or
over
maybe
here.
that's just the mount.
Oh, she's my favorite teacher.
But there's gotta be. You know, the whole thing was to get this thing spinning fast enough. So the electricity came in.
Only because of.
Did Joe take his?
But I don't.
Yeah, he was.
See, the only thing I can think is it came
Joe say
here.
what?
It came
Did
in
Joe-
here.
Yeah, it's taking.
But it doesn't cross over into those
Did
copper
Bo take it
wires.
too?
I
It
think
never
so.
crosses over into those
I'm gonna
copper
be
wires.
alone in my math class.
How about
I'm gonna. What is this called? I'm gonna just look it up and see what pops up on the online, just to see if it shows me anything. Well, I know, but
Sears Kenmore.
Sears. How you spell Kenmore?
100 Kenmore.
Kenmore.
Or like Monday or something.
1.2 amp, model 5187.
1.2 amp.
Model 5187.
Believe it or not, the older they are, the easier they are to find online. Is what, like, if ever you look up a new car model, they're like, it gives you everything. But if you look up old car models, they're like, why am I getting? I don't know who that is. Here we go.
Legit,
So,
every single person in our friend
in Lord.
like we all, I love
That's not the same one.
And you see post on story.
It looks pretty close.
Pretty close, but this,
They would be made similarly though, because they're made.
they're all made the same.
Right.
That's it right there.
Get the. Why do I'm just gonna click on it and see what it takes me to, because it took me to the it's only showing you this side of it. Did you bring that black piece? Here we go.
Yeah.
Here we go.
And he's like, yeah, whatever.
Yeah, like you don't have to.
You don't get the other
So,
side.
I don't know why you use
Like,
it.
he was-
It's connected. It goes around to the other side,
6, 7, 8, and 9.
and it's.
Coach Silva.
I think is that mount? No, it's not sitting on there. Actually, the other way around. That flip it over. Because if you see it, because it was sticking out this way, and then it would be going in on this side, because it goes around.
No, he was in the hospital for a long time, but then he got out and he had problems.
Yeah, because it's so it looks like so it looks like it might go into those because it's going right around there, but then it looks like it's going that way. It doesn't go straight down to here. It goes more like there. But that could be the in, that could be the out. Once it reaches to the top, it could come out the top, go in the bottom.
I understood what you said,
Because
but I
in the similar way with the plug, the mount of the plug is also the conductors.
Can you understand it?
probably a little bit.
Let me see what else. See if we can get it.
I couldn't do that to anybody.
French is crazy.
Model, that wasn't the right model.
No, it's not. Oh.
Model 1120, we want model 5187.
Please, be friends. All of us need to be friends with them.
I tried to be friends with him just because.
I mean, but it might just be. It would probably still be similar.
And then this year we really just pushed them out.
That's the sewing machine right there. I can tell you that.
I'll see if they decide to show you the components. Because sometimes they will.
No, I couldn't make it that night.
It was where you.
No,
It was. I think it was a game.
No, 67.
Yeah, against the.
Even if it's a year off, it might still.
Yeah, it was when
Could just be the year of bought necessarily.
Oh, yeah.
They don't show any income inside.
And we had Clay and Ocean.
Model 5187.
He said it somehow. He put a picture in between me and that. I was like, bro. And he was like,
What was that?
That's one fighter.
Sears Kenmore. Did you put in Sears Kenmore?
Yeah.
So you just hold
Let's see what else is. I'm gonna see 50 volt 50 out of the
Actually, it would always be that, because that's just telling
Yeah,
you what it
110,
is.
120, that's just telling you.
Even though, like, that would be known with the model, so it would be irrelevant. Yeah, here we go. 5187.
Alright, so which angle are we looking at?
Oh, well, since we don't see those, it would be, turn it, no, because,
That way.
there you go. That's how it happens.
I
Before you see the whole end of the top there.
No, I said,
It's going around the back.
it was me and.
So, probably here. But it would be unusual for it to screw in, and there's no grounding in between here. So maybe there was one that was between here.
I said, hey, it's okay. Just take her from me.
Okay.
It was funny.
That's it.
Did they take that off, or is that actually, did they take that part off, or is that?
I'm sure it's there.
Yeah,
Sure,
he left
fine.
it.
Dude, we should go watch planes.
Yeah.
Like, we should go for school watch planes.
I want to fly with
Yeah.
him.
No, you know, like,
I have a heart attack, but I want to fly with him.
you know, when he goes to Columbus Airport and sits there and watch planes.
Oh, I thought he flew.
You said
He goes and sits there for viewing.
He has flown, actually.
Yeah.
I want to go.
We should go sit there and watch it with him.
He's watching the planes, we're watching Hayden watch the planes. It's like that one, it reminds me of that one meme where there's a guy sitting there and then there's people to the shooting about
Do you
the
have
guy.
him on? Do you have him on Snapchat?
No.
Do you have Snapchat?
I don't like it. I delete it. I don't use it, and also I forgot my username, so.
I believe what happened.
I can't even get mad at him.
What must have worn it out.
I mean, to be fair, it's for him. It's probably like watching races, like you just like watching it, or like an air show. Think of it like an air show.
He just watches. No, he just
There's
goes
just
there.
a tiny little bit of
Exactly, it's like,
movement in it.
Like he just watches.
And that probably.
Yeah, it's like think of it like an air show.
You can look on here and you can
Like that's
see
entertaining.
where
Air
it was
Yeah,
contacted.
he's very
It's
smart.
not supposed to contact. See where it contacted
He's so
down inside? And it's not supposed to contact.
So wiring came loose and made contact and then short circuited.
Something caused it to contact. See that shiny right there?
If it wore down, it would just break and then short circuit itself, wouldn't it? So
And if
just
it contacted, it would short circuit itself.
and that's what would cause this.
But it doesn't take much movement. Now, there's a question. Put it in there.
So like there's those frayed wires, which I think.
That probably happened.
And then he runs to the bathroom and slams the door.
The frayed wires could have caused it, could it? Because when it frays, it makes contact. It's hitting something.
So sad.
It's not supposed to be hitting that, is it?
It's hitting something.
I think it's one of those. It's probably one of the copper wires because copper wire comes, uses, frays, makes pops
Who does?
open, makes contact with it, short circuits
Just
this
to
side.
like outlift some boys. Yeah, I'm gonna outlift some boys.
So it might be just replace all those copper wires.
That's one for the girls.
You're gonna outlift
Some girl will
Lucas.
probably outlift me.
He's gonna outlift nobody.
Who's gonna outlift
What
you?
about that?
Because that's,
Probably on bench.
For what? Yeah, bench.
I mean, that's all
I
wrapped.
can do
That's
legs.
a
I have
curved
really
magnet.
strong legs. I
Are you
have
going to
strong
do?
arms.
You can do
That's
flat.
all wrapped with copper
I can
wires.
squat.
Pull
I
that up
can.
and then
And we've got copper wires.
How much do you
Have you
weigh?
ever tried to
we
do?
can take it out easy.
180.
Copper.
I can squat one.
I bet this
Little
next
tax
match we're probably getting 315.
I bet my deadlift
Or
is
maybe
500.
pull it out. And then would we need to
Dude, I'll
solder
do
it,
leg press.
or is it would it hold?
Yeah.
I love lift press. That's my favorite.
Leg press is so easy.
Wraps.
Still, it's an ego lift.
The solder's
Me-
down there in the back.
Trey and Johnny were in Mercedes.
See where it's soldered in right
And
there.
we went.
That goes round and it's soldered in right
Trey
here.
pumpkin.
How much
So-
do you
Trey Van
need?
Dyke and he moved.
I've got tons of it back there.
Oh.
Do you
I
want
think
to
we have
start
it.
working on that, or should like
No, not right now.
Let's go ahead and take it out.
But it's definitely a project. I don't want to take it apart until we get ready to do it.
Well, obviously, Trey
That's what I was
too
joking.
many
That's what I was joking.
steroids.
Actually, I
Red.
no.
I just meant the copper bit.
Rip does not mean you can lift the most.
Yeah, if you're ripped, that means you have a low body fat percentage. And you know that people that look ripped are actually fully weaker.
Oh, actually, yeah, like at those muscle shows like that Arnold Schwarzenegger does, like
That's bodybuilding.
yeah, bodybuilding.
And you got powerlifting. Those dudes are
No,
big.
bodybuilders, they are like they're so weak.
And then
They
because
just,
their body fat percentage is like
faint.
4%, 3%.
Yeah, I know, but they like starve themselves.
And that
they,
low,
they
that
have
low
like
health.
zero everything.
So
I did like 10 reps. But like people like Brian Shaw.
and it's
Like, it gets to the point where I could beat them in a fight because they're like they can't do anything because they're that weak.
over there too.
That's strength. Other people are bodybuilders. I'm Claire, I need Molly. You can always squat the bar. People think like
That's only 45. I can do
yeah,
that.
at least you know it's 45. Yeah, wow.
I don't like the way that sounds.
Since I did,
What is
I
it?
can do it. Yeah.
What are y'all even doing? Because I saw y'all in there. I saw some volleyball.
I could make it
people
with
working on
Boston
there.
Power.
Almost
For every shake, couldn't I?
So we do like.
How powerful
No, we
would
do
that
like-
be?
we do- we
Make
have
one
one
off
day
of a
arm
water
day,
wheel,
four
too.
day.
Which would be more powerful?
Dude, I'm so.
How much water you got?
Well, the water wheel would just would be a slow spinning. It wouldn't be I would need high torque. I wouldn't want consistency. I would just want a spur of energy.
I just want
A water wheel would just
Like, you know how
wouldn't be a spur of energy. It would just be
I feel like I can't do that.
slowly going.
I'm so
Whereas
sore.
if I could do it with an engine, I could build it up to a high speed,
That's how I
like
feel.
fifth, and then once I put it in fourth gear, or depending on how many gears I have, when it gets to the fourth gear, it then connects.
So there's no bearing.
And then it has
I usually have a game on
There's
the
no
wall.
actual bearing
I don't
down
understand why
inside of it.
baseball starts so early.
Or is there an actual bearing that is?
Most schools don't. It's just, you know, if you want to be good, you have to work.
You want to
So we're
All
working.
year round.
You can't work out for 3 months and take 9 months off. You want to
Okay,
get
but I'm
stronger.
saying like
You'll
do
get
it.
stronger that 3 months and you'll lose all the muscle.
Start in like November, not
Claire, that's how like.
August.
They already have their schedule. Claire, you like.
There's no
I had a
bearing
lot more
in
muscle
anything.
during wrestling season, but then
So
I
run cross
we
country,
stopped
I
wrestling,
can't
and then I
just
had surgery,
stop
which I just
running.
sat around for a week.
You'll lose your muscle.
Yeah, and that's also how I lost like 20
year.
pounds.
And then just run again.
Every time after like Connor, that's how Connor got to
You should
114,
run.
and then went.
No, I don't like running. I'm good at short distance running. I'm not good at.
Yeah, just do a bunch short distance back and forth a bunch of times.
So you should join track.
You should run.
Track is.
If we had a track team.
We do have a track team. We just don't have a track.
What the heck?
Exactly. Thank you. You don't get it
If we
either.
had a track.
We don't have a track.
Okay, when we get a track, I'll join.
We're not going to get a track.
one by next
I want to do those ones where you jump the thingies.
We
Yeah,
have a hurdle. We're gonna have a hurdle.
Because we're just not going to host it. We just can't host.
Who's your?
You don't jump them, you hurdle them.
Okay, can I hurdle some hurdles?
It's more because you never jump straight up. It's all you feel like you're running
You're
motion.
like running.
Sandra beat me.
It was one of the. What was it? That's one thing.
We just can't host any. We can't host any.
I don't
tournament.
remember.
We'll all be away.
I know
because we don't have
Timothy
this.
Mullins
Yeah,
is pretty good at it.
Did y'all play cross country meet at Shaw at Connect Stadium yesterday?
That's what I'm on the cross country meet yesterday.
Why was there was at Connect Stadium yesterday? There was a cross country meet.
They just followed me.
They didn't look like middle school, and then middle school said they were somewhere else. But there was a cross country meet. at Connect Stadium. Wait, do y'all only do your category? It just does cross country have category? Like okay, so that
It
might
goes
be what it is.
1A private,
No.
7A public. We are 1A private. We are literally the smallest. Like, if we were to compete against a 7A public, we'd all lose. Actually, that's not true.
Well,
it would be like our top 2 runners maybe would beat some people.
The thing is,
But
here's how you could also look at it. At private schools, they look at the public schools and go, hey, you're pretty good. We'll give you a full ride scholarship to our high school.
Jonathan,
And then they get all the best schools at the private school. That is a possibility of happening. I'm not saying it does happen, I'm saying it could happen. It probably has happened.
Why do you think Trinity's so good at football?
Is Trinity a public school or private? Where?
Trinity's in our region.
I don't know.
Like our region for
We have
cross
I know
country.
Trinity Drive.
Our Trinity for cross, like our region for cross country is literally just us, Trinity,
It's because
Brookstone, and then there's Heritage.
So
that's it.
But my point being that a public school, even though a 1A could still be the 7A if they have given full right to all who would be on the 7A scheme.
So yes, in theory that could happen, but in practice it doesn't.
That's still not gonna be.
They're still not gonna be literally the biggest. So if you think about it this way, it's just the pool of people you get to.
Yeah. I know. In the public school, it's going to be like, hey, I want you. Come here.
You have to be relatively smart.
Yeah. Because if you think about it in terms of like, so let's say one runner out of 100 people can run faster than, like, so let's say 7-minute mile is average. So one runner out of 100 people is faster than average. So we get
and the average person is below average intelligence. Yeah, it's actually
that doesn't make any sense.
Neither does any of our political system. But here we are.
Jonathan.
I'm not making political.
No, Jonathan just doesn't understand the definition of the word average.
Average is the thing
is the midpoint between the total. Therefore, 50% of people are worse than average and 50% are better.
No.
By definition.
No, that's not true. If you have outliers, if you have a constant, if you all only have outliers. If you have someone with 1,000 IQ, and then you have a bunch of people with 20 IQ, the average person is 50%, and then on this.
So you're telling me that in the world there are people with 700 IQ and none of them with 12? No. Because that's what you would have to have.
I'm not saying it's impossible. I'm just saying
they are. Jonathan.
And also, IQ is not a constant form of measuring, seeing as different IQ tests are measure different things. And also, IQ is a measurement of a specific skill set. It is not a measurement.
How are you measuring intelligence?
Exactly.
You are so stupid right now.
No.
Yes. You just said the average person is less intelligent than the average intelligence, and then you just argued that you can't measure intelligence.
Yes.
That makes no sense. You are part of that average, if that is true.
No.
Yes.
No. Sam. Trey.
Oh my god.
Arguing is fun.
When we first came,
Can I punch him?
But
if I punch him, will you report?
Yes, I would have to.
I've actually kind of thought, like, if I was to do anything to anyone, I would, like, this is the class to do it in.
No, it's not.
You can't have an IQ without
And just, but here's the other thing. But here's the thing. How can you measure, how can you agree that one person has a higher IQ than the other when they took two different tests?
It's okay though, we're really good friends.
You see my point?
Do me a favor.
Our solo should not.
No, well,
by yourself.
Because if you had a constant IQ test, then you could study, then you could practice, and you could memorize all the answers, and therefore it wouldn't be a study of your IQ.
This conversation.
It's just an exercise.
Because
It's an exercise.
I am not a video.
Bro, Bill has a funnest.
It is a debating exercise. That's all I'm doing.
Jonathan, it's not the numerical values that matter, it's the median and the average and the midpoint that matter, and the standard of deviation. They use a different IQ test for each study, but they don't compare studies. They compare each of the individuals within a study, which is why you can say the average IQ for this study is X.
And are we assuming that the people chosen have been chosen as the average people and have a group of people representative of the whole rather than choose?
Jonathan's trying to argue that there's human bias, but when you have a study with hundreds of thousands of people, it's unlikely that there's a error in the
selection process of who's going to take the study.
If they were all white males over 50, then there would be an obvious bias. But they were not all white males over 50.
our government is all white males over 50.
How did we go from IQ to government like that?
Because you mentioned white males over 50.
Actually, it's not.
Okay, there is some acceptance, but most of them. 98, okay, yeah.
It's actually pretty representative.
Yeah, I would say modern day it's not as true.
Well, we still have the age is still the age of the
Yes, because you legally cannot be a politician
until you're 36.
Well, I just got it.
Name a 36-year-old president. Actually, how old?
John F. Kennedy was 38.
I know. I just thought of him. I know.
And are you kidding me?
How many times did John F. Kennedy? How long was John F. Kennedy president? Exactly. They don't.
Oh yeah, and Abraham Lincoln was assassinated too. Abraham Lincoln wasn't important?
No,
Editor error.
I never said that. Why?
Well, you were just arguing that because John F. Kennedy was assassinated 2 years into his presidency that he wasn't important.
No.
That's literally what you just implied.
No, what I was implying was that they don't want that making a conspiracy that the government doesn't like white males under 50.
Yeah, they're.
Miley's long for like Chase.
They're on for Chase you?
Yeah, she's so young and
Hillary
She
Clinton.
didn't have her mask on.
How about
She is a woman.
Yes.
And she was the Democratic candidate.
Yes, and was she elected president? I'm just making a stupid point at this point. Purposely stupid.
Can you stop?
Just
silence.
Anyway,
No more.
I still
words
think our
out of
steam
your
engine
mouth.
should be it should still use the steam engine to go in to do the DC router thing and then make that DC router power a pump to power a combustion engine. Because then we can get
Enormous waste of energy.
Mallory says,
If
"Oh,
Once wrestling season starts, and I come in just to
This is the
one day
weirdest
so I
thing.
can beat him into submission.
She says y'all.
Will you let me?
The way she said it, y'all.
If you drop 20 pounds,
y'all."
10 pounds.
No, I'm just
10
gonna
pounds. Drop 10 pounds and
That's
I'll
just
do
how
it.
she talks.
No.
10 pounds.
Do you really
No deal until you drop 10 pounds.
I said no. I'm running cross country.
How much do you weigh?
Right now I'm 160.
Get to 150. Get to okay, never mind. 20 pounds. Go to 140. We're good.
I should have some
150, 140. Get in between there.
He doesn't like
130.
He thinks he weighs 130.
No, I do. Where's the scale?
Why do you
It's
say
in the one trip.
Is that above or below average?
No, I don't. For my height, I have no idea.
It's way below average.
Yeah, because I lost 20 pounds.
Right.
And I really doubt that you maintain
Yes.
that loss of 20 pounds over months of doing nothing.
Nah, surprisingly. I know I'm actually also not eating much either. Up for months.
You
I was going
just let
to.
people wait and
Because
I know.
I want to go to second.
And then as I have started to use more energy, I've started to eat more.
Do what?
Chicken down.
Yeah, chicken out because
Chicken
everyone
out.
was
Wait,
there.
you were
I was as surprised as you were, and then I had my own way to stand on the scale, and he's like, "Oh no, it's
Yeah, I could.
that's accurate," and I'm like,
Too long for me.
"All right."
That's what I remember.
But I did it. I
Did he? She wasn't.
But it's already cool. But if you can
So,
find
What do you
another
like
scale, I'll
know
stand on it.
movies?
So like.
I don't know, so I might be a little more.
Addie was my girlfriend. Addie was my
It should be about 130, 133, 130, like 135 max.
So like after I texted her, I was like, thanks for doing that. She's like, yeah.
Don't touch me.
So.
Don't touch.
I used to tell Claire all my time.
Not
Yeah.
That's there's only two people I told her girls, Claire and Claire. So, no,
Did I ever tell you like in September I was like, remember that photo?
See, now my brain is
Boys are so
I'm so
terrible.
She literally tried to call me. She's like, never gonna.
I just get.
This is like
I enjoy mind games.
And then
I just, I do.
December.
Not all of it. No. Like
So
I
she's like,
skipped
I
3
don't know
questions.
if we should play. I was like,
And then she got
like
very
who?
mad at
She
me.
like two?
One of you was on work.
Every time.
I answered these.
One of you was on work.
Every time.
I answered these.
What are you trying to
Here, they are so mean.
Hey, you got
I actually
it.
started with
class.
I got chill.
Sounds like it's in,
I'm used to it.
in the half.
No, they're like
In
rude.
this half.
I did like the instant ones first.
And as soon as I said anything, I'm like, man, I should have said that. Because
Yeah, but it was
Definitely like in the middle
I
region.
should have said that.
Wasn't there one about like because I only skipped one of the
It's just
like
an
expanded
enclosure.
answer.
What?
Wasn't there one about like
No, because
drawing
when we showed when we pulled up the picture,
what was that about?
this was completely open.
I didn't read it either.
Going around the back.
She showed us how to do it, but I forgot. The combustion reaction though is just spreading out.
It's the only place for it to come in.
And then the cheese.
I don't care.
Oh, yeah, it was about a combustion reaction.
Yes, yes.
So yeah, we were. So
You
when she
write
started, we
out
were talking
the
about
equation.
dance.
Wait,
Combustion always
unless
spreads.
that thing there,
And I was like, yeah. And I was like,
right there is supposed to go into that hole.
Yeah, it is. And I was like, yeah.
Yes,
That's
always.
one thing.
Did you have one of those?
As soon as I said that, I was like, no, she said that. And every single person.
Equals CO2 emissions.
And even Miss Queener got it. I was like,
It was
tight.
cute, and then we were like,
Nah,
she was like, so does she like you?
I know.
Okay, but Lana, it's like Johnny and Joe.
I
Ghost like a kind of ghost that have a boat.
I know how to do the book one, but I'm not sure how to do it for a combustion.
Because they,
I think it's.
And then I think it went.
If not, then I'm gonna cry.
yeah.
I'm gonna cry.
They were such a good
But I
job.
know Johnny does
Combustion reaction.
He likes his land.
Oh, I see.
The only people that I think the only person that
You know, wasn't everybody come on my land, probably not for the Chaco game, my land is very two tractor. I can see it from my land, but.
Yeah, that's what I thought.
I got pants.
Okay, I understand.
What?
I understand.
Oh, did you do the
I did most of it. I
Did you know one of the very
I've
bottom?
also been that. I did everything except for the final question.
I can, still got another baseball.
Yeah,
That's the only one that I I think I did it right,
Check out
but
Arlo
I'm not
Lunch.
entirely sure.
And that's what I was gonna do. This year.
Me and Mia were thinking about it, but I don't.
I did not.
Wait, y'all checking out to go to lunch?
No, I'm checking on the go.
I think I did it right. It's
Get out of here.
Oh my
I don't have my.
It's not too bad.
I have.
Like you just have to.
Like 5 minutes ago. What are
You just have to stretch my hooves. Wait, we can leave?
What?
Time of value is.
Time? But there were no values on the bottom.
Changing T means changing.
That's.
ISIS.
I'm stupid.
Changing time is.
Y'all have a good lunch.
You too.
Changing time's physics.
ISIS.
You were in chemistry, weren't you?
ISIS, you need to look at the side of the graph. It says, it gives a reference. It says T and then parentheses degrees Celsius.
I was doing physics and chemistry.
You might want to just make sure because we might have different tests, but.
No, I think we're
No, she
talking
was
about
doing
the same
physics and
question.
chemistry. That's what it was.
You okay, brother? You messy. I'm messy. What happened? Shania. You messy. Third period? Oh, I almost called that.
I asked her, I was like, why are they calling you my name? She's like, I'm not asking the same question. I was like, I don't even ask.
Run me on one. I'm tired of this.
You won't learn this one when you do shit.
Run me on. Oh, you talking that?
You ain't do shit wrong. She called me a bitch.
Okay, anyway. Run me on one. Run me on one. Run me on one.
Oh.
One good time.
No, it's not.
I know it's not.
So what are you doing in my classroom?
Alright, so move. No, because you don't got no shirt on. Oh, yeah. Hey, want to see some ass? Want to see some ass?
I'll get ready to run in 4-4 today.
No, because you come here.
How were they? Never paid attention to coach. How were they?
Oh, there you go. You've already known about the run, probably 4 weeks.
Yeah, right?
I'm gonna go to a food home again. I'm just food going starving. You know, I've never ate 5 pieces of pizza in my life. Just Jameson let us put it in her refrigerator.
Recipe for success already?
Yeah.
There you go.
Don't come in here if you're not in my class. Go where you're supposed to be. Maybe I got it today. I got less, y'all, less. All right. Let's see, Taylor's at home. Frank. Here. David. Hernandez.
Here.
DeWitt's at home. Kite's here. Bobby.
Here.
Lisa. Shania.
Yeah.
Aiden.
Here.
Hunter and Mark.
Here.
All right. Wow. What do y'all want to do? I planned on something, but
Watch a movie.
yeah,
Watch a movie.
Watch a movie.
Let's watch a
science movie.
Yeah, science movie.
Physical science. Physics.
No, I'm not gonna take a nap. If I show a movie, y'all gotta stay awake.
Yeah. Alright.
Alright?
Right.
And everybody's gotta move over that side of the room, because Ms. Collins will come in and look in and see us watching a movie, and everybody's not doing what they're supposed to be doing. Then I'll get in trouble, and then I'll be mad at y'all.
You're in trouble for what?
Everybody's gotta move this side of the room.
Yeah, but move over here. You're good. Just, hey. Do that. Hey, you two up front. Dude. Hey, wake up. Hey, you dude. Move over here. Not all, you don't have to move all the way that line. Just move over to the side. Move over.
What's the reason of this?
Because I said so. Yeah, you don't have to move out. You just move over to one of these 2 rows. You're good right there. Yeah, you're good right there. You're good right there. This is asleep right there. Wake him up.
Hey, Daniel.
Move over. Alright. Go sleep. See what I can find.
Alternate 4, 5, 5.
Huh? Now watching Kim Al-Jalil Gravity. Pretty cool. This guy does some of the best physics stuff on YouTube. He does some pretty cool stuff. Lots of physics. Don't go. Keep your heads up. Don't keep your head up. I'll give y'all an essay to write.
Whoa, now.
Yeah. Keep your head up. Let's see.
Would you like to lose a little bit of weight without doing any exercise or dieting? Would you like to age just a bit more slowly than your friends? Well, you might be surprised to hear the laws of physics can help you. The key to unlocking these everyday questions is gravity. It sculpts the universe. It warps space and time. It's a fundamental force of nature. But gravity's strange powers, discovered by Albert Einstein, also affect our daily lives in the most unexpected ways. In this film, we'll be using cutting-edge scientific techniques to investigate how gravity changes your weight. It's gone up. Your height. I really have shrunk. And even your posture. And with the help of thousands of volunteers, I'll show you how gravity makes us all age at different rates.
During the day, I've just been logging onto the phone, logging onto the app.
As a physicist, gravity is central to my work. Oh, wow. And in exploring it, I'll be challenged on how I understand this most mysterious force. Wow. Okay, I need to go and write this one down. And I'll have to tackle the very nature of reality itself. Gravity. It binds together all the matter in the universe, and it makes our existence here possible. But in the end, it all boils down to one simple question. What happens if I drop an object? gravity's many mysteries are all contained in this single action: how an object falls. Here's the first puzzle. Why does a hammer fall faster than a feather? You might think it's because the hammer is heavier, but that's not the real reason. The answer is air resistance. It's not the weight of the objects that matters, it's their shape. And I can demonstrate this very easily with these two umbrellas. They both have exactly the same weight. But if I open one of them, you can be pretty sure it'll drop more slowly than the other one. In fact, all objects would fall at the same rate if you could only remove the air. The first person to realize this was the 16th century mathematician Galileo Galilei. Famously, it's said he worked it out by dropping objects off the Leaning Tower of Pisa. And he was spectacularly proven right in an experiment carried out on the moon in 1971.
Well, in my left hand I have a feather. In my right hand a hammer. And I'll drop the two of them here and hopefully they'll hit the ground at the same time.
It worked perfectly.
How about that? That proves that Mr. Galileo was correct in his findings.
Now Galileo was obsessed with a second question too. When you drop an object, it's actually quite hard to tell if it falls at a constant speed or picks up speed as it drops. Even in slow motion, it's pretty hard to tell. But Galileo realized this. First, drop an object a very short distance. It lands with very little impact. But of course, drop it from higher up. This time, the ball easily breaks the tile, which means it must have accelerated, gaining in speed and momentum as it dropped. Galileo had identified something fundamental to all falling objects. They accelerate. He realized there might be a way to measure how much falling objects gain in speed. What he devised was the first ever attempt to measure gravity itself. He built a long wooden ramp, rather like this, that he had sloping at a shallow angle. The idea was to roll balls down the ramp and measure their acceleration. The crucial thing is that the ramp had to be at this shallow angle to reduce the effects of wind resistance. It also meant that the balls would roll down slowly enough to give him time to measure their speed. But the big problem was this: how do you measure time accurately in an age when there were no accurate timepieces, let alone stopwatches? Well, Galileo came up with an ingenious idea involving the flow of water, essentially measuring time from the amount of water collected in a cup.
I showed y'all this before.
So we're going to try and repeat Galileo's experiment. I say we because I have a couple of willing volunteers, Gavin and Joanna. 3, 2, 1, go. Get ready, because Data in Science is here. GenerationGenius.com educates and inspires students with free. Stop. Okay, there's one. Now, if you come down a quarter of the way down the ramp, go. Stop. Okay, so now half of the way down, go. Stop. Okay, and then 3/4 of the way down. Go. And stop. Right, turn the tap off. Okay, so we have our 4 measurements, and I can see a progression from fuller to emptier. But what we need to do now is find the mathematical pattern by weighing carefully the water in each glass. Weighing the water should give us an idea of how long each roll took. And in our experiment, these were the results. Now there's one immediate thing you can tell. The ball really sped up the longer it rolled. In fact, our results seem to show that the time it took to cover the first quarter of the ramp was about the same time it took to cover the next 3 quarters. So we have a strong hint of a mathematical pattern. Now we'll see if we're right by placing bells along the ramp at intervals which are based on the results. This arrangement looks a bit strange because the gap between the first 2 bells is much shorter than the gap between the 3rd and 4th bells. But that's okay, because if we've got our calculations right, the ball starts off slowly, so it covers a shorter distance, and as it picks up pace, it'll cover longer and longer distances. So we should hear the bells ringing at equal intervals in time. Go. Beautiful. So, what does this all mean? What's the mathematical formula? Well, this is something that Galileo worked out. Let's say, from the start, the ball covers a distance of 1 meter in the first second. After 2 seconds, it'll have covered 4 meters. After 3 seconds, 9 meters. After 4 seconds, 16 meters, and so on. If you recognize this progression, you'll see that distance goes like the square of time. Galileo had found the rate at which gravity speeds up objects. And he'd found another fundamental principle. You can measure the strength of gravity by how much it causes falling objects to accelerate. Detecting gravity has become exceptionally sophisticated these days, but still uses exactly the same principle. This is Hurstmonceux Castle in Sussex, and in its grounds lies the Space Geodesy facility. Here, Vicky uses an astonishingly sensitive instrument to detect the exact strength of gravity on this one spot. Okay, so Vicky, tell me about this incredible gravitymeter that you work with.
Okay, so this is the drop-in chamber in a stripped-down version. So essentially what happens is you've got a cart that gets raised to the top, and then the cart accelerates away from a mass in the middle. And so this section here lifts off, and as it drops under free fall.
So this component in the middle, as it drops, is basically just Newton's apple falling to the ground.
Yes.
So this is a stripped-down version, but that's the real thing.
This is the real thing.
How does it actually work?
In here it's a vacuum.
So there's no wind resistance.
So there's no wind resistance.
Right. Inside, a laser is used to measure exactly how fast the mass is accelerating. This is the 21st century version of Galileo's ramp and the ball's rolling down. So can we get it going?
Of course, if you just like to press the button on the laptop.
This one?
Yep.
Okay.
So it's now communicating with it.
Oh, here we go.
There we go. So it waits 5 seconds, then takes a measurement of gravity.
And repeats. Oh, and you can see all the results appearing now.
Yep. Each of those green dots is a measurement of gravity with the actual number that it's getting for each one.
The unit Vicky uses has a familiar ring. I see that the number up at the top here, so you've got this unit, microgal.
Yes, gal is essentially 1 centimetre per second squared. The gal was named after Galileo.
So we've just taken the measurement of gravity here today, and it's this highly accurate number, 9811240007 microgals. The reading means that the Earth's gravity speeds up a falling object by around 9.81 meters per second for every second it drops. Vicky tells me something intriguing. She takes a reading here every week, and she's found that the strength of gravity changes by tiny amounts over time. Heavy rainfall, for example, can cause gravity to increase slightly. Presumably, if gravity is changing here in one spot, it will have different values all around the world. And so you can have a gravity map of the entire planet.
That's right, yeah.
So what's the reason for these strange fluctuations? That's what I want to investigate next. So, gravity changes as
Build custom industrial machines in days. Design your machine in the simplest online CAD. Get inspired by our public designs. Or build your own in minutes.
as we move across the surface of the Earth. Well, this lies at the heart of a challenge that I've set two young volunteers. I've given them a task to try and find a place in Britain where gravity is at its weakest, so where objects will weigh the least. And I've given them just 3 days to try and find it. The volunteers are Estrella Sendra, a PhD student.
I've been living in London for 5-6 years, and I'm originally from Seville in Spain. I'm very interested in taking part in this project because I would really like to know more about how this world works.
And Poppy Begum, a journalist who lives in London.
I did my degree in biomedical science, and I did biology and chemistry for my A-levels, but I haven't done any physics since I left school. I'm fascinated to find out more about gravity, and I actually enjoy a puzzle. I like a challenge.
Now, the team can't just weigh themselves to see changes in gravity. Body weight fluctuates naturally by a couple of kilos over the course of the day, whereas changes due to gravity, if they travel around the country, are going to be tiny in comparison, a matter of a few grams. So they're going to have to use sophisticated scientific methods if they want to measure gravity accurately. And that's why the volunteers will be joined by 3 specialists in gravity science. PhD student Sonak Bose. He'll be in charge of some very sensitive measuring apparatus from the National Physical Laboratory. Sean Hughes, a geologist, who'll be using a portable gravity meter. And Andrew Ponson, a cosmologist at University College London, who'll help interpret the results. We've taken a collective weight for the team before they set off. It's 380 kilograms. So, can they find a place in Britain where that'll decrease? They're setting out in Snowdonia National Park in North Wales. The railway climbs from here to the 1,000-metre summit of Snowdon. Sean takes his first gravity reading.
The inside is a mass on a beam, and you turn this counter, this dial, until you get the beam central.
By counting the number of turns of the dial, Sean can calculate the downward pull of gravity acting on the mass inside the machine. Sonak has a simpler method.
So inside the box is a 2-kilogram mass, and it's supposed to be sort of as perfectly 2 kilograms as it's possible to get. Alright, and place it here.
Oh, it's just coming under, isn't it?
1998.2 grams.
So it was 2 kilos in the laboratory, but now here it's a bit less.
It's the first puzzle. Why does a 2-kilo mass tip the scales at just under 2 kilos? And it's one which gets straight to the heart of what the challenge is really about. Mass is often confused with the related quantity, weight. The mass of these dumbbells is fixed, it doesn't change. It's a measure of how much stuff they contain. Weight is different. It's a measure of the effect of gravity on these dumbbells, the downward force pulling them to the ground in the same way that it's keeping my feet firmly stuck to the ground. The crucial difference is this: if I was holding these dumbbells on the moon, they'd still have exactly the same mass, but they would weigh 6 times less because the moon's gravity is so much weaker than the Earth's. So that's why Sonak's bringing along the 2-kilo mass. If it changes weight, then this should mean that gravity itself has changed. Ahead of them is the summit of the highest mountain in England and Wales, famed for its stunning scenery. Or it would be stunning if you could see it.
And this is what we came all the way up here for. This amazing view at the top of Snowdon. You wouldn't know it, but honestly, we are here. So we're now near the summit of Snowdon, and I've set up the gravimeter again, and we're going to see what the difference in the reading is.
He has to turn the dial again and again to try and get a reading. It's clear gravity has changed, but which way? Has it got stronger or weaker? The team leaves Sean to work out his results and tries to position the scales as close as possible to the summit. But the reading is all over the place.
Oh,
It's gone up.
it's fluctuating quite a lot due to the wind. I have to say, this is what science is always like, isn't it? It's never quite what you want it to be.
So they head inside to the cafe next to the summit.
The wind was being a bit naughty, but hopefully.
It's zero, so it should be alright.
1998.2 down there. 1997.8. We got it.
That's 0.4 for gravel.
The mass weighs a tiny bit less. It's lost about 1/5000th of its weight. And Sean's found that gravity itself has reduced.
At the top of the mountain, we took the measurement, and we discovered that the pull of gravity had gone down.
Good grammar and spelling are important, but if you want to write essays that inspire, messages that forge brighter connections, and
it had gone down an equivalent of 206 turns of the dial, and we worked out that that's equivalent to 219 milligallons.
So it's clear from the team's measurements, gravity weakens as you go higher and you get a bit lighter.
It's just an excuse to say where are we like the lightest, who cares? But in the sense that it's actually really interesting. It's like an illustrative example of seeing how this is actually fluctuating depending on different factors.
Yeah, absolutely. And that we could measure it and we could see it with our own eyes. It actually makes you think about gravity in a very active way. It's such a fundamental force phenomenon in nature, but we don't know that much about it.
But why does gravity change with altitude? To understand that question, you have to get to grips with the extraordinary discoveries of the next scientific giant in our story, Isaac Newton. Born in England in the middle of the 17th century, he spent his life wrestling with so many apparently separate questions, from why things fall to the ground to why planets orbit the sun. It took the genius of Newton to realise that there was one single equation that could answer all these questions. And here it is, his famous law of gravity. It might look complicated, but this is one of the most important equations in the whole of science. F here is the force. Now, Newton said there's an attractive force between any two objects in the universe. On this side of the equation, G we call the gravitational constant. Now, Newton knew it had to be there, but he didn't know what its value was. M1 and M2 represent the two objects, and R is the distance between them. Now, the equation tells us that the more massive the objects are, the bigger M1 and M2, the greater the attractive force. But the further apart they are, the bigger the value of R here, the weaker the gravitational force. With Newton, what was once mysterious now became clear. Newton's equation describes why an object falls to the ground, including his famous apple. But its true genius is that it applies to any object, anywhere in the universe. So it's a very simple and elegant way of describing some of the seemingly most complicated phenomena in the cosmos. His law of gravitation can still be used today to explain how orbits work, to predict when a comet will return, to describe why galaxies spin, or to slingshot spacecraft around planets. Newton tells us to look for the underlying simplicity in natural phenomena, For instance, how the moon orbits the Earth. If I let go of this apple, it'll fall straight down because of the pull of Earth's gravity. But if I throw it, to begin with, it travels in a horizontal direction, that's the direction of travel, but Earth's gravity is still pulling it downwards, so it ends up following a curved path. Now, if I throw it harder, it'll travel further before it hits the ground. And in principle, if I could throw it hard enough, I could put it into orbit. And that's exactly what's happening with the moon in orbit around the Earth. It's a combination of wanting to travel in a straight line, but also being pulled down by the Earth's gravity. So it ends up constantly falling around the Earth and constantly missing. Newton's famous equation also explains the strange effects which the road trip team has discovered, that objects get lighter as you gain in altitude. When I weigh myself, I'm represented by the first mass, M1. The second mass, M2, is the Earth itself. And the force pulling me down, my weight, depends on the distance between me and the centre of the Earth. And that's the secret of the road trip. If you want to find a place where you weigh the least, then you have to get as far away as you can from the Earth's core. So it's the afternoon of day one, and the road trip team have to work out where to go next. Poppy and Estrella have a good idea. Find somewhere higher than Mount Snowdon.
From the measurements that you guys did at Mount Snowdon, altitude clearly plays an important part in gravity. So with that in mind, we've got to go to the highest point in the UK, which is Ben Nevis.
Okay, but there's just one thing that we haven't shown you so far. We actually brought along an extra experiment. So can we please show you this first before you make the final decision?
Yes.
Sonak actually has the other parts of this experiment. We always carry around
some power tools, as physicists always do. So let's start off nice and gentle. Okay, and then try and pick up some pace.
Pizza.
Improving.
The point is that when something is spinning, it kind of gets flung outwards, and you can actually use that to make a nice flat piece of pizza. But this also applies to the Earth.
The Earth isn't perfectly round. It's... Get ready, because Data in Science is here. GenerationGenius.com educates what's known as an oblate spheroid. It bulges at the equator where the spin is greatest.
We've kind of got two competing effects now. We're trying to get away from the centre, the actual core of the Earth, the point at the very centre of this ball. But now we can do it in two ways. We can either kind of go up something tall, or we can just go down towards the equator.
Because what we find when we're doing gravity surveys is that as you move south, there tends to be an effect from latitude, which is often usually larger than the effect from altitude.
So the closer to the equator you go, the further you get from the Earth's core, and the lighter you get.
So, guys, the sun's setting just behind me here. This is north. From the conversations we've just had, it sounds like we've got to go that way down south. Is that right?
Yep. Okay, let's go.
Let's go.
The team is starting to uncover the reasons why gravity changes as you cross the surface of the Earth. Our planet is defined and shaped by the complicated forces which act upon it. And detecting tiny fluctuations in its gravity field can give us important clues. It can help us understand how our world is changing. The Space Geodesy Facility at Hurst-Monceau is one small part in an enormous global network, which uses satellites to detect the tiniest of changes in the Earth's gravity field.
Tell me what exactly your job is here. What we're doing with this telescope is measuring very accurately the distances of satellites from here. So we're using very short laser pulses, which we direct towards the satellite. On the satellite there are reflecting cubes, which return some of that light to us. and we measure how long it takes the light to go to the satellite and back.
And how far away is the satellite?
What we're tracking now is one of the Galileo satellite, which is about 20,000 kilometers.
20,000 kilometers
Yes.
away?
Yes.
Okay, so we've got it aimed at the Galileo satellite, and you're going to turn the laser on now.
Yes.
Oh, wow. And that laser beam is being fired up towards the satellite.
Yeah.
How the time it'll take to get there and come back again, it's a fraction of a second, isn't it?
It is. It's about 150 thousandths of a second, 150 milliseconds. And we're sending about 1,000 of those per second.
This strange-looking object is based on satellite readings. It's a highly exaggerated representation of how Earth's gravity field varies over time. Fluctuations like these can give us important insights into climate change. Ice caps melting, sea levels rising, changes in groundwater. All of these have an effect on the local strength of gravity.
So something as important as climate change, in order to understand it and do something about it, we need to know the distribution of the gravitational field of the Earth very accurately.
Absolutely, yes. And it's a global measure that we need.
For the road trippers, it's the start of day 2. And they're heading for the south coast. They're stopping off in Herefordshire. It's a good location, as it's the same altitude as the base of Snowdon, but they've moved about 18 miles further south. So, if they find gravity changes here, it must be due to latitude.
It's not a huge difference, but it's noticeable. Our counter reading at the bottom of the mountain was 4,840.
Yeah?
Our counter reading here is 4,717.
Alright, so you do get to see a difference.
So we're actually at the same altitude as the base of Mount Snowdon, but because we've travelled further down south overnight, gravity's less here.
Yeah.
They push on. And by sunset, they reach Sidmouth on the south coast. Sean takes the second gravity reading of the day, and Poppy improvises a map. Well, sort of a map.
We might not to scale at the top there. So I drew this map. Scotland's a bit squashed. Wales is quite high up, and Cornwall is there. But you get the idea. So Sean, we've been travelling with you. You've done quite a few gravity meter readings. Can you plot them on this not to scale badly drawn map, please?
Sure. So if you remember, we started off in Mount Snowdon, about here, and that was the 0 measurement for our survey. And then we've come all the way down here to the south coast. The difference from the base of Snowdon is minus 212 milligauss.
Wow.
So the difference between measuring gravity at the base of the mountain and the top of the mountain is about the same as here at this latitude and down here at this latitude.
They're quite clearly at sea level, yet gravity here is roughly the same as it is at the top of Snowdon. But where next?
We are here. If we want to find out where we are the lightest, why don't we travel all the way to the most southerly point in the UK, which is here?
But altitude can also help us. So why not find a place in the country that is both low in latitude, but also is high in altitude in terms of height above sea level? Because that will get us somewhere that is really far away from the core of the Earth, while staying within the country.
So, the answer to the puzzle lies in a combination of two factors. How much further south should they go, and how much higher? At the end of day 2, Sean's results show that the team weighs about 80 grams lighter in total than back at the base of Snowdon. The way that weight changes is just one example of Newton's famous equation in action. But Newton had left his masterpiece incomplete. He didn't know the value of G, the gravitational constant, which sets the size of the force. To harness the full power of the equation, you need to know G. And the vital clue came with an incredible experiment conducted in London at the end of the 18th century. It was an attempt to work out the mass of the Earth itself. And it was carried out by an eccentric, extravagantly rich aristocrat, Henry Cavendish. Cavendish was a chronically shy, deeply solitary man living in total isolation in his house in Clapham. The story goes that one day he accidentally bumped into a female servant on his staircase. He was so traumatized by this event that he had a new staircase built just for him, so this horrible incident could never happen again. Cavendish had inherited vast fortunes and was able to dedicate his life to devising pioneering experiments, including one particularly extraordinary piece of equipment. He set up something a bit like this. It's called a torsion balance. It involves 4 lead spheres, 2 large heavy ones which are held fixed in place, and suspended by a very thin wire is a wooden rod, 6 feet long, with 2 smaller balls on either end. Now, the crux of the experiment is the relationship between the large ball and the small ball. Now, of course, there's a gravitational pull downwards on both of the balls due to the Earth's gravity. But Newton also tells us that there should be a very weak gravitational pull between the balls. And this is effectively what Cavendish was trying to measure. Any slight movement of the small ball towards the large one should cause a twist in the torsion wire. And that's what Cavendish was trying to detect. Of course, this is all much easier said than done. The experiment was incredibly sensitive. The tiniest of vibrations, the slightest breeze, changes in temperature could all influence the measurements. So Cavendish had to isolate the apparatus inside a box and the box within a shed. He even realized that his mere presence next to the apparatus could influence things, so he had to remove himself outside the shed. What he then did was sit outside the shed and through a small hole in the shed wall, look through a telescope to detect the tiniest of twists in the wire. It was an incredibly difficult process, but after many months, he finally felt confident enough that he had a reliable result. Cavendish found that the small balls did move. A tiny 4 millimeters. He calculated his results by comparing the density of the balls with the density of water. In the end, the result of Cavendish's experiment and subsequent calculations was that the density of the Earth was about 5.5 times that of water. Or, put another way, the mass of the Earth was 5.9 trillion kilograms. What's most remarkable is that Cavendish got this number right to within an accuracy of 1%. With Cavendish's astonishing result, scientists were able to work out G. Then the equation could be used to determine the mass of any celestial body in orbit around another. So astronomers were able to calculate the mass of the Sun, and the planets, and the Moon, and eventually even distant galaxies. And of course, back on Earth, we never escape gravity. Over the course of the day, it actually squeezes your spine, an effect you can see for yourself if you use a measuring rod. Okay, so it's 7:30 in the morning, I've just got up, and I'm going to see how tall I am before gravity drags me down. That's 178 centimeters, or just over 5'10". Over the course of the day, gravity compresses the fluids in your spine. Right, it is just past 11 p.m. I've been standing up for most of the day, so let's see if gravity has had an effect on my height. That is 176 centimeters, so I really have shrunk by just over half an inch over the course of today. In the longer term, gravity can affect your posture permanently, but there are exercises you can do to counteract this effect.
Part of my research has been looking at the effects of gravity on the human body. So people might not be aware, or they might not always think about the effect of gravity on our physical state, on our health, and particularly on our posture. However, because it's such a constant force, gravity has a massive impact over the course of our lifetime.
As you get older, you can develop a stoop, which is damaging to your mobility.
Doctor here has actually got very good posture, but I'd like you to just show not so good posture. So when poor posture is really rounded shoulders, and then lots of the curve in the back as well. I can't just ask you to raise up your arms when you're in that posture. So no, and then just come back down, shoulders back in front, and then raise your arms. You can see the effect of posture on function.
Ironically, the exercises which many gym goers do actually make your posture worse. That's if you only exercise the frontal muscles, like the chest and abdominals. So it's recommended you exercise the back muscles just as much, to straighten you out and counteract the effects of gravity. Meanwhile, it's the end of day 2 for the road trip, and they've reached Sidmouth on the south coast, looking for the place in Britain where they'll weigh the least. They've worked out the answer lies in a combination of 2 factors: the right mix of going south and being higher up. And for the final leg of the journey, I'm going to meet up with them. I asked them to drive a short distance west, to one of the most remote areas in mainland Britain, Dartmoor National Park. It's only 40 miles from the southernmost tip of Britain.
Hello, nice to see you.
And it's very high, very hilly territory.
Jim, the team got to the south coast yesterday to find gravity at its weakest. But we haven't quite figured out whether it's altitude or latitude. Do we go further south or do we go higher up?
You're right to ask, do we go as far south as possible or as high as possible? That's why I've brought you here to Dartmoor. And we've charted the most important points on this map here.
Alright.
Let's have a look. So we are here, 2 bridges.
Yep.
These 4 dots represent these hills up there behind us, which are at about 500 metres above sea level. So that's what we want to check out. These hills are close to the south coast, and they're also the highest in the whole of the south of England. So logic suggests there must be the right combination of latitude and altitude.
Well, there's another reason why this makes perfect sense, one which we haven't looked at yet, and that's the effect of the underlying rocks on gravity. And I've got a map here that shows...
You're going to trump my map.
Here we are, down here. These blue areas are the lowest areas according to the density of the rocks underneath.
The rocks around here are made of granite, which will make gravity weaker still. So that's helping, as well as the altitude and the fact that we're further south.
Yep, to also play a part.
Well, we have a plausible theory, but now we need to test it. If I'm right, then at the top, our gravity reading should be by far the lowest reading of the trip. Of course, there's another effect of gravity to deal with now. It's knackering when you head uphill. Okay, so I think this is pretty much the start of the hills we've located on the map. So let's see if this is the lightest place. Sean, if you want to get the gravity meter out, and we'll take another reading here.
Yep.
Okay? Sean sets up his equipment one more time. What's the news?
Well, at the bottom of Mount Snowdon was our zero for this test. We found we lost a certain amount by going up to the top of Mount Snowdon. We found we lost a certain amount coming south to the south coast. Not only have we beaten that, we've smashed it.
Brilliant.
We were minus 219 milligauss and lower at the top of Mount Snowdon. Here on Dartmoor, we're minus 347 milligauss and lower.
Brilliant. So it is a combination of three things. We're far south, so it's the latitude. We're at altitude, look at high up, and we're surrounded by all this granite rock, which is low density anyway. I hope you all think it was worth the climb up here anyway. Yeah. There you go. Boom. Science. Now, we already know that the altitude of these hills takes us much further from the Earth's core than anywhere else further south in Britain. So gravity must be weakest here. There's extra evidence too. The British Geological Survey has compiled tens of thousands of gravity readings made in the UK, and the lowest readings ever recorded were all taken around here, on the high hills of Dartmoor. What do we do to celebrate? We weigh ourselves, of course.
Ja, thanks so much, so much.
It's all ended up selling pancakes for breakfast.
I can tell you that you should weigh something like 20 grams less than you did at the base of Mount Snowdon. Guys, I'm guessing something like 25 to 30 grams less. So, if you want to weigh as little as possible, this is the place in Britain to come. But in any case, it's such a tiny amount that it's going to be wiped out entirely by whatever it was you had for breakfast this morning. In episode 2, I'll investigate how Albert Einstein's theory of gravity completely changed our understanding of space and time.
You like went over mine.
Yeah, the little whole roll.
I was like, we did this. We talked about this. Time to go get out. Because we ain't got no bills today. 108. Spray down the table. Go grab your stuff. All y'all's classes been like this? Nobody in here?
Four people are really.
Nah, just wait.
Come on, you can feel the pressure.
Hey, y'all have a nice day. Stay out of trouble. Do anything stupid.
Wait, what?
Why'd you taking SAT sincere?
When am I?
Huh?
You said when am I?
I said, why aren't you?
Take your last minute and go.
Yeah. Don't go that far. I missed it. Don't go that far. See, they don't go that far. Yeah, you missed. Go pick it up now, boy. Nigga, they don't go that far. You see what I'm saying? They don't go that far. Niggas are hooper and stuff. Hell no. You brick? You can sit backboard. That's my end. He really made it dinky back up.
It's not for more budget.
He breaking off another piece of shit. Niggas. Another brick. That nigga's a hooper. He's a hooper. I'm glad we put our BSP. He's trying to make that shit heavy.
J Cloud's up there.
Niggas.
On this.
Are we learning about the carbon cycle?
We watching a video today, boy.
Oh shit. So that's it. Kim Al-Jalil. Kim Al-Jalil.
I was gonna say amazing word of gumball.
I mean, it definitely, it says amazing word of gumball, but it says Kim Al-Jalil.
It says amazing word of gravity.
This is a name, right? I said, yeah, I saw that, and I was trying to say the name. Kim Al-Jalil.
Kim Al-Jalil.
Jalil.
The physicist.
Is he Arabic? Arabian?
It's English, actually.
English?
Yeah.
Does he come from Arabia? Right?
Yes. What's up, y'all?
Watching the video too? Question?
Crazy, bro.
Wow. Let's see who's here first.
Yeah.
Let's see, Kenny's here. He's here. Cole. Crawford.
Online.
Oh yeah, he's online. Anissa.
Here.
Nick.
Here.
Faith.
Here.
Yeah.
Here.
Elijah. Mine. Luke. Here. Reed. Lowry.
Online.
Lowry's online?
Yes.
That's right. This is the class of a bunch. This is Quavion.
You checked out.
You checked out. Ariana.
Here.
Caitlin.
Here.
Oh, it's coming in. There's online. Solomon. Here. Albert.
Here.
Here. All right. All right. Let's see. All right, we're gonna take these from yesterday, and we're gonna do some more stuff with them. So, Luke, Canyon. Caitlin. Name. Kevin. Let's see, Sincere. Casey. Faith. Mia. Oops. No name. Nick. Ariana. Connor's not here. Lawrence not here. Vanessa. Let's see, Justin, Taylor, Hayden, Frank, Ben, that's the other class. Does everybody that was here yesterday get theirs back? Yes? No? You can get yours? You weren't here yesterday? I'm going to give you one. All right. Now, all of these problems that were on there yesterday can also be solved by graphing. All right? Everything on here can be solved by making a graph. You just got to know which graph to make. All right? Just got to know which graph to make. Let's see, that's not it. It is. Nope, that's not it. The wrong one. And if you know which graph to make, depending on which what you're trying to find, and what numbers are given, you can actually find out some more stuff. All right, graphs are extremely useful. Now, for the first one, well, we're just measuring distance. All right, we don't need the full 4-quadrant graph. All right, so when we have just distance, with a starting point, all right, with an x initial and an x final, all right, we only need one graph. And there's a couple of different ways we can do this. We can do a motion diagram. We can do a particle diagram, or we can just graph out our 0 point and our end point, right? And what do we have? 12 total. So I know my end's 12, all right? And then we just kind of got to break it into 12 equal sections. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I've worked that almost perfect. I know my end point, right? I know my zeros over here, so I simply need to go 1, 2, 3, 4, 5. There's my 5 point. Then I can just count it up, right? 1, 2, 3, 4, 5, 6, 7. All right? So I know my x initial is here. I know my x final is here. All right? And since distance is distance. It's a positive number. It's a scalar. All right? And I don't have to have a direction with it. All I got to do is know the absolute value of the difference in my position. Okay? So it started at 5. Okay? We know it was moving somewhere. All right? It started at 5. It ended at 12, and all we got to do is count it up. So you can use a graph just to get that same information. So graphs can be really useful, and it is perfectly okay on a test if you can graph it and do the same thing. There's nothing wrong with that. All right? There's nothing at all wrong with that. So you should have gotten 7 meters, right? I believe was the correct answer on there. So check yourself, look on there. Did you get 7 meters? All right, the second one asks for speed. All right? And we have a distance and a time. All right? So we have an x position. All right, which is going to go on our vertical axis. Time only goes in one direction, right? Probably should make that a little bit taller. All right, and how many seconds was it going? 15 seconds. So I'll make these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
Will it matter?
All right? There's my 15 seconds. Do what?
That's will it matter? Probably solve it on a test.
Does it matter what?
Probably solve it on a test. Like if you
Yes. Yes. All right? Now, to make my graph, do I want to do these in ones? I could, 15 and 30. I can easily do that. Remember, these are squares, right? These make perfect little squares as they're supposed to. What do I want to do to kind of get that angle? Do I want to make each one worth 1? Probably not. I probably want to go make them worth 2. Maybe even 3. Okay? So we'll make this 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. All right? So I know my initial time is 0 because I'm not given a time. All right? I'm only given that it's moving for 15 seconds. So my point on my timeline is at 15. All right? And if each of these is worth 3, all right, I simply come up, there's my distance I traveled. Now I come across, go up, and I know that my point of 30 meters in 15 seconds are going to intersect right there. All right, now I can draw my line. All right, now I can draw my line. Now, this is going to tell me a couple things. All right? First of all, my speed is going to be the slope of my line. So the easiest thing to do is find places along this line where you're going to have seconds, and one of my verticals, anything that's on my vertical here, hit a corner. All right? Because my speed is going to be the slope of my line. All right? So on a distance versus time, or is this velocity or just distance? This was asking for speed, right? Yes. All right? So if it's speed, my speed is going to equal the slope of the line on the graph. So a good place, and I'm going to tell you, it's obviously going to cross at 2 and 6. Should cross at 2 and 6. All right? And I know that 6 divided by 2 is 3, right? Is that what we had? What was our final here? It should have been 2. Yeah, 6 divided by 3 is 2. All right, so it should hit 3 seconds. And it did. Oh, there we go. All right. And I can find my slope right here is going to be at 6 and 3. 2 and 3. 2 and 6. All right. Slope of my line. Write it out. All right. It's going to give me 2 meters per second. All right. Because for every second, it's going 2 meters. 2 meters, almost a 3 right there. Almost to, it should be about 5 and some change right there. Right there, it's going to be at 6. All right, so it's 2 meters every time it crosses one of those second lines. So I know that my slope here, all right, is going to equal my speed. We can do the same thing for velocity. All right, now this velocity question was a little bit different though. All right. What was I given here? What is the velocity of a ball traveling 40 meters to the right in 5 seconds? That was the same problem. Same thing. Now, with speed, I don't have to look at which direction it slopes. All right, with velocity, I do. All right, and I have to look at where it is because speed is going to be the absolute value of the slope. All right, and I probably should write that up here. Absolute value. With velocity, the angle of the slope matters. All right, so if I get, and obviously ours was a positive slope, right? Went in this direction. But if I get a negative slope, all right, where we end up at 0, start out up here, I'm going to end up with what? Okay, so let's reverse everything on this problem. I have 40 meters to the left. This is my position right. Okay, so we'll start it at 40. All right, 0 minus 40 meters over how many seconds? 5 seconds is our time, our change in time equals 5 seconds. All right, 0 minus 40 is negative 40. All right, negative 40 divided by 5 is negative 8, right? Meters per second to the left. All right, and what I would need to know here is that my initial starting position was at 40 meters, right? My final position, my x final, is at 0. All right, so in this case, all right, we're not moving to the right, we're moving to the left. All right, so the slope does matter. The slope does matter. All right, and it's going to change the problem entirely. Our case, we had just a positive slope. And if the slope goes below the line, well, you've changed directions. All right? Displacement. let's see, displacement of a ball. All right, and we're asking for a what? What type of quantity is that? It's a vector, right? Therefore, I'm going to need direction. I know I'm going to need direction with it. All right? So, displacement of a ball traveling to the east at a velocity of 20 meters per second for 11 seconds. Now I've got a velocity versus time graph. All right? So now I can label this velocity. This is always going to be time. All right? Let's see, how far did it go? 20 meters? So we'll make these 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right? Now, we're asking for displacement. We know it went for, how many seconds to go for? 11 seconds, sorry. Went for 11 seconds. All right? And so that's my line for my time, right? And it went 20 meters per second. So that's where they're going to intersect. All right? Now, this is what the cool thing about a velocity versus time graph. The area is now going to be displacement. Right? The area of that is going to equal our displacement. All right, I'm sorry. Our area is going to equal our acceleration. Oh, oops. All right. The area of my parallelogram, however, is going to equal, sorry, remember the parallelogram rule, right? And the area of my triangle here is going to equal my acceleration. And since we're working with average acceleration here, it'll tell you about how fast it's accelerating. Same thing here as with others. All right. If we reverse the angle, then we reverse our velocity. All right. If something is moving towards an area, okay, this is in the positive direction. If it has negative velocity, or moving away, okay, it is going to move this direction, all right? It's going to be in the negative direction. It can start anywhere on here, all right? Position, remember, can start anywhere. Time is always going to start at 0. We just got to know where we're measuring from, all right? So if we're moving away from something, even if it's here, even if we start at 0 and run 20 meters south, okay, this is going to be negative direction. If it is increasing in the positive or slope up, it is going to have positive direction. Even if it starts down here. All right? So we can tell the direction by the slope of the angle, the slope of our line. Now, with acceleration graphs, we use velocity. All right? In this case, we used average velocity. So, it's not a very straight line. We'll take that straight down. And since we've got a very large number here, I'm going to make my graph a little bit higher, okay? So my 0 point is where I can understand it. Now we'll make these 5 miles an hour. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90. Does that have fast we accelerated to? All right, and we've got 5 seconds, so I'm going to make these probably a half second. Okay, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. All right, so those are 0.5 seconds each. Takes us out to 5 seconds. All right. Now, where is my starting point on my graph now? It's at 45. So 5, 10, 15, 20, 25, 30, 35, 40, 45. All right. Where is my ending speed? It's at 90, right? So it's all the way up here, 50, 55, 60, 65, 70, 75, 80, 85, 90. All right? So I know that's my end point. All right? I know that's my start point. I know I am going to cross at 5 seconds. So from my start to my end, all right? That'll give me my average right there, and it will give me the average acceleration. And once again, you know, this is very easy to figure out, okay, because I have a velocity initial, all right, and a velocity final. It all adds up. Another cool thing about these is we can figure out how far the car traveled, how much area, how much total area is under the slope of the graph. All right? Because we have a parallelogram here, we have a rectangle. And we can tell what the size of a rectangle by adding up its, multiplying its 2 sides, so 5 times 45 is a lot, all right? The area of a triangle is 1/2 my base times my height, right? So we can actually figure out how much area, how much distance it covers as well by using the our a little bit of graphing power, all right? Questions about any of that? Did y'all have any questions on that yesterday?
No, sir.
All right. Everybody get the right answers? Get all everything labeled? Yes? I think y'all did pretty good. You know, I saw some things we're going to have to work on, but that's okay. That's why we're here. That's why we're here. I don't expect you to know it. It's my job is to show you how to do it. All right, so I'm going to show you how to do it over and over and over and over and over until you get it right. All right. Hadn't done a lot. Have we done any graphing in yet? A little bit. Not much though. All right. Get used to drawing graphs. Graphs are important. All right. As we go, we'll do more and more graphs. We'll start adding a lot of our formulas together. And eventually we'll be able to get them into the 4 formulas that we need to where we can figure out anything. All right. And there are 4, formulas that if you know those formulas, and I'm not going to make you memorize them in this class, but if you know how to apply them, you can pretty much find out anything as long as speed is constant, as long as acceleration is constant. All right? But they're simply by putting these formulas together. All right? Questions? All right, I'll let y'all watch the Kemal Jalil. It's good, it's gravity. As long as y'all keep your heads up, nobody goes to sleep. Go to sleep, you got to write an essay. All right, I'm going to have those back. Now, one of you drew a graph on there.
I do it on the other paper.
Okay.
Oh, did I get that?
That's right. I just wanted you to see them while we were going. I just wanted you to be able to look at them while we were doing them. Yeah, because I didn't put them in the grade book yet.
Wait, do we have to draw it on that paper?
Do what? No.
Oh, because I drew it on a piece of paper.
I would have, personally, I would have drawn it on the same piece of paper since we were doing the same problem.
I just drew it here.
All right, let's see. You just want to write an essay? What I say? Heads up. Y'all want to watch this? You got to keep heads up. All right. Thank you. Anybody else I didn't get your paper back from? I hadn't put them in the grade book yet.
But gravity's strange powers, discovered by Albert Einstein, also affect our daily lives in the most unexpected ways. In this film, we'll be using cutting-edge scientific techniques to investigate how gravity changes your weight, your height, I really have shrunk, and even your posture. And with the help of thousands of volunteers, I'll show you how gravity makes us all age at different rates.
During the day, I've just been logging onto the phone, logging onto the app.
As a physicist, gravity is central to my work. Oh, wow. And in exploring it, I'll be challenged on how I understand this most mysterious force.
Wow. Okay, I need to go and write this one down.
And I'll have to tackle the very nature of reality itself. Gravity. It binds together all the matter in the universe and it makes our existence here possible. But in the end, it all boils down to one simple question. What happens if I drop an object? Gravity's many mysteries are all contained in this single action: how an object falls. Here's the first puzzle. Why does a hammer fall faster than a feather? You might think it's because the hammer is heavier, but that's not the real reason. The answer is air resistance. It's not the weight of the objects that matters, it's their shape. And I can demonstrate this very easily with these two umbrellas. They both have exactly the same weight. But if I open one of them, you can be pretty sure it'll drop more slowly than the other one. In fact, all objects would fall at the same rate if you could only remove the air. The first person to realize this was the 16th century mathematician Galileo Galilei. Famously, it's said he worked it out by dropping objects off the Leaning Tower of Pisa. And he was spectacularly proven right in an experiment carried out on the moon in 1971.
Well, in my left hand I have a feather. In my right hand a hammer. And I'll drop the two of them here and hopefully they'll hit the ground at the same time.
It worked perfectly.
How about that? My conclusion that Mr. Galileo was correct in his findings.
Now Galileo was obsessed with a second question too. When you drop an object, it's actually quite hard to tell if it falls at a constant speed or picks up speed as it drops. Even in slow motion, it's pretty hard to tell. But Galileo realized this. First, drop an object a very short distance. It lands with very little impact. But of course, drop it from higher up. This time, the ball easily breaks the tile, which means it must have accelerated, gaining in speed and momentum as it dropped. Galileo had identified something fundamental to all falling objects. They accelerate. He realized there might be a way to measure how much falling objects gain in speed. What he devised was the first ever attempt to measure gravity itself. He built a long wooden ramp, rather like this, that he had sloping at a shallow angle. The idea was to roll balls down the ramp and measure their acceleration. The crucial thing is that the ramp had to be at this shallow angle to reduce the effects of wind resistance. It also meant that the balls would roll down slowly enough to give him time to measure their speed. But the big problem was this: how do you measure time accurately in an age when there were no accurate timepieces, let alone stopwatches? Well, Galileo came up with an ingenious idea involving the flow of water, essentially measuring time from the amount of water collected in a cup. So we're going to try and repeat Galileo's experiment. I say we because I have a couple of willing volunteers, Gavin and Joanna. 3, 2, 1, go. Stop. Okay, there's one. Now, if you come down a quarter of the way down the ramp, go. Stop. Okay, so now half of the way down, go. Stop. Okay, and then 3/4 of the way down, go. Stop. Right, turn the tap off. Okay, so we have our 4 measurements, and I can see a progression from fuller to emptier. But what we need to do now is find a mathematical pattern by weighing carefully the water in each glass. Weighing the water should give us an idea of how long each roll took. And in our experiment, these were the results. Now there's one immediate thing you can tell. The ball really sped up the longer it rolled. In fact, our results seem to show that the time it took to cover the first quarter of the ramp was about the same time it took to cover the next 3 quarters. So we have a strong hint of a mathematical pattern. Now we'll see if we're right by placing bells along the ramp at intervals which are based on the results. This arrangement looks a bit strange because the gap between the first 2 bells is much shorter than the gap between the 3rd and 4th bells. But that's okay, because if we've got our calculations right, the ball starts off slowly, so it covers a shorter distance, and as it picks up pace, it'll cover longer and longer distances. So we should hear the bells ringing at equal intervals in time. Go. Beautiful. So, what does this all mean? What's the mathematical formula? Well, this is something that Galileo worked out. Let's say, from the start, the ball covers a distance of 1 meter in the first second. After 2 seconds, it'll have covered 4 meters. After 3 seconds, 9 meters. After 4 seconds, 16 meters, and so on. If you recognize this progression, you'll see that distance goes like the square of time. Galileo had found the rate at which gravity speeds up objects. And he'd found another fundamental principle. You can measure the strength of gravity by how much it causes falling objects to accelerate. Detecting gravity has become exceptionally sophisticated these days, but still uses exactly the same principle. This is Hurstmonceux Castle in Sussex, and in its grounds lies the Space Geodesy Facility. Here, Vicky uses an astonishingly sensitive instrument to detect the exact strength of gravity on this one spot. Okay, so Vicky, tell me about this incredible gravitymeter that you work with.
Okay, so this is the dropping chamber in a stripped down version. So essentially what happens is you've got a cart that gets raised to the top, and then the cart accelerates away from a mass in the middle. And so this section here lifts off, and as it drops under free fall.
So this component in the middle as it drops is basically just Newton's apple falling to the ground.
Yes.
So this is a stripped down version, but that's the real thing.
This is the real thing.
How does it actually work?
In here it's a vacuum.
So there's no wind resistance.
So there's no wind resistance.
Right. Inside, a laser is used to measure exactly how fast the mass is accelerating. This is the 21st century version of Galileo's ramp and the ball's rolling down. So can we get it going?
Of course, if you just like to press the button on the laptop.
This one?
Yep.
Okay.
So it's now communicating with it.
Oh, there we go.
There we go. So it waits 5 seconds, then takes a measurement of gravity.
And again. Oh, and you can see all the results appearing now.
Yep. Each of those green dots is a measurement of gravity with the actual number that it's getting for each one.
The unit Vicky uses has a familiar ring. I see that the number up at the top here, so you've got this unit, microgal.
Yes, gal is essentially 1 centimetre per second squared. The gal was named after Galileo.
So we've just taken the measurement of gravity here today, and it's this highly accurate number, 981124007 microgals. The reading means that the Earth's gravity speeds up a falling object by around 9.81 meters per second for every second it drops. Vicky tells me something intriguing. She takes a reading here every week, and she's found that the strength of gravity changes by tiny amounts over time. Heavy rainfall, for example, can cause gravity to increase slightly. Presumably, if gravity is changing here in one spot, it'll have different values all around the world. And so you can have a gravity map of the entire planet.
That's right, yeah.
So what's the reason for these strange fluctuations? That's what I want to investigate next. So, gravity changes as we move across the surface of the Earth. Well, this lies at the heart of a challenge that I've set two young volunteers. I've given them a task to try and find a place in Britain where gravity is at its weakest, so where objects will weigh the least. And I've given them just 3 days to try and find it. The volunteers are Estrella Sendra, a PhD student.
I've been living in London for 5-6 years, and I'm originally from Seville in Spain. I'm very interested in taking part in this project because I would really like to know more about how this world works.
And Poppy Begum, a journalist who lives in London.
I did my degree in biomedical science. I did biology and chemistry for my A-levels, but I haven't done any physics since I left school. I'm fascinated to find out more about gravity, and I actually enjoy a puzzle. I like a challenge.
Now, the team can't just weigh themselves to see changes in gravity. Body weight fluctuates naturally by a couple of kilos over the course of a day, whereas changes due to gravity as they travel around the country are going to be tiny in comparison, a matter of a few grams. So they're going to have to use sophisticated scientific methods if they want to measure gravity accurately. And that's why the volunteers will be joined by 3 specialists in gravity science. PhD student Sonak Bose. He'll be in charge of some very sensitive measuring apparatus from the National Physical Laboratory. Sean Hughes, a geologist, who'll be using a portable gravity meter. And Andrew Ponson, a cosmologist at University College London, who'll help interpret the results. We've taken a collective weight for the team before they set off. It's 380 kilograms. So can they find the place in Britain where that'll decrease? They're setting out in Snowdonia National Park in North Wales. The railway climbs from here to the 1,000-metre summit of Snowdon. Sean takes his first gravity reading.
The inside is a mass on a beam, and you turn this counter, this dial, until you get the beam central.
By counting the number of turns of the dial, Sean can calculate the downward pull of gravity acting on the mass inside the machine. Sonak has a simpler method.
So inside the box is a 2-kilogram mass, and it's supposed to be sort of as perfectly 2 kilograms as it's possible to get. Alright, and place it here.
Oh, it's just coming under, isn't it?
1998.2 grams.
So it was 2 kilos in the laboratory, but now here it's a bit less.
It's the first puzzle. Why does a 2-kilo mass tip the scales at just under 2 kilos? And it's one which gets straight to the heart of what the challenge is really about. Mass is often confused with the related quantity, weight. The mass of these dumbbells is fixed, it doesn't change. It's a measure of how much stuff they contain. Weight is different. It's a measure of the effect of gravity on these dumbbells, the downward force pulling them to the ground in the same way that it's keeping my feet firmly stuck to the ground. The crucial difference is this: if I was holding these dumbbells on the moon, they'd still have exactly the same mass, but they would weigh 6 times less because the moon's gravity is so much weaker than the Earth's. So that's why Sonak's bringing along the 2-kilo mass. If it changes weight, then this should mean that gravity itself has changed. Ahead of them is the summit of the highest mountain in England and Wales, famed for its stunning scenery. Or it would be stunning if you could see it.
And this is what we came all the way up here for. This amazing view at the top of Snowdon. You wouldn't know it, but honestly, we are here. So we're now near the summit of Snowdon, and I've set up the gravimeter again, and we're going to see what the difference in the reading is.
He has to turn the dial again and again to try and get a reading. It's clear gravity has changed, but which way? Has it got stronger or weaker? Easily shown to work.
Did I just spray you down, man? You got no funk, no germs, no ringworm, no reddish rash, no shoulder pad rash. You'd been miserable if you had shoulder pad rash. You're having 3 days. Time y'all get out 12:03. Oh, they got the bells back on. All right. Y'all have a great day. Stay out of trouble. Don't do anything stupid. See you. You good?
Hello, everybody. So, how you doing? Today was so pointless. Why did they make it so pointless? I don't know.
Yeah. Yeah.
Last period, I read about
Do what?
last period, I read
I'll be here after school today.
tomorrow at lunch.
Tomorrow at lunch. I'll be here after school tomorrow.
I'll do tomorrow at lunch. I'll do tomorrow.
Do you say you won't be here
I
tomorrow?
won't be here tomorrow because we have a factory.
It's only Wednesday.
We do.
Well, it's really Friday. Not going to do Friday. I haven't done anything today, like actually. I finished my homework for me and math.
Or I'll figure out something else for you to do between now and the end of the period.
Okay. Can you just not today?
Hey, kids! What's up, Cole? Bo?
Carolyn, she took the SAT and she went home.
Who?
Carolyn took the SAT and then she left that day.
Did you come back?
Nope. Can I go to the bathroom?
Yes.
Bill Nye.
Who am I missing?
Carolyn, Bo. I don't know where Natalie is. I think she's here, but I don't know where she is.
I think she took it.
Maybe
Natalie took the SAT.
She took it. She wasn't in my first period.
Okay, I kind of graded these. I just kind of went over them, looked at some things. Jan?
Are you putting in the grade book?
Not yet, I hadn't. 'Cause we're gonna play with them a little bit more. What did I tell you this is? Probably what? Practice. Caleb Perry's not here. Oh, there you go. Thomas. No, Thomas is here. Carlos. Austin. Mercedes. Natalie Morgan.
Thank you so much. Oh, no red. Oh, wait, yes, red.
Yeah, red's not bad. Everything's red. All right. So, what we have, a couple things I just kind of want to go over. There are other ways to do these. You can solve these with graphs too. All right, and I know we haven't done a ton of graphing in here, but you can solve every one of these with a graph. Now, the first one is the simplest one. All right, our first one is our simplest one because it's just a straight line. All right, and you could do this with a. You could do this with a particle a particle graph or a particle diagram or a motion diagram. It would be the same. All right. But all we've got to do, and since we only have one variable we're dealing with, what was my last number on there? 12. Okay. So we could start at 0, 1, 2, 3, 4, 1, 2, 3, 4, 5. All right, we know our final stopping point is 12, 6, 7, 8, 9, 10, 11, 12. All right, and I know now that that is the distance that I need. All right, between 5 and 12. So then all I got to do is count it. 1, 2, 3, 4, 5, 6, 7. and I know that I've moved 7 meters. All right, that's the simplest one. All right, but you can always use a graph on any of these. On my second one, what does it say? I want to know the speed. All right, so I've got to know what I'm looking for. I want to know the speed. So I've got a vertical line that's going to represent my displacement or my distance, and a horizontal line is always going to be time. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 seconds was total, right? I can make these 2 seconds each. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. All right? Was 30 my distance I needed? All right, so each one of these is equal to 2 meters. All right, each one of these is equal to 1 second. All right? Did I give you yours back?
Yeah, what are you doing?
Huh?
What are you doing?
I'm not done with them yet.
Oh.
All right. Now, I can do the same thing here. I know that I've moved 15 for 15 seconds. Okay, so I can count it out to 15. And there's my vertical component. All right. Or sorry, my horizontal component. And then my vertical component is up here at 30 meters. And I know that they're going to meet right there. Now, I can go anywhere along this line, and the slope is going to tell me the speed. All right? Slope of the line will equal speed. And I can find that anywhere on here. All right? I can find that anywhere on here. It's going to be 2 over 1. All right? So that's going to give me 2 meters per second. Doesn't matter where I go. I can find any point. All right? If I go to 2 seconds, 2 meters in 1 second. That one's going to be 4 meters in 2 seconds. It's going to be the same. Because 4 divided by 2 is 2, right?
Yeah.
That's what we came up with. It's 2 meters per second, right? So it's going to come out the same. All right, so we can use the slope of the line to find the speed as well. All right? What's the next one? Next one I'm finding what?
You're finding the velocity.
Am I finding the velocity? What is the velocity of a ball traveling 40 meters to the right in 5 seconds? So my displacement component is going to be here. Time is always going to be vertical, or sorry, horizontal. I don't know why it says vertical. And we've got 5 seconds, right?
Yeah.
So I'm going to make these 0.5. 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. And then it's going how many meters? 40 meters. So 5, 10, 15, 20, 25, 30, 35, 40. All right? Now, once again, do these dotted lines remind you of anything? Any other rule we use? Parallelogram rule, right?
Oh, yes.
Yeah.
Definitely.
All right. Well, parallelogram rule works out again. All right? Because if we find this total area right here, we're going to find our displacement. All right? We were looking for what though? What were we looking for? We were looking for velocity. So once again, velocity is going to be our slope. All right? Velocity is going to be our slope right here. And what we'll get is going to be about 8. All right. So should work out fine for us about 8. Let's see, there's 1 second. Yep. And it works out to just under, and that didn't draw too bad of a graph there, Coach Anderson. All right. But you can also use, and the best way to do it is find a place where both of them hit a corner. Anywhere the line hits a corner, that's an easy place to figure out what your slope is. Because then you've got a whole number over a whole number, and you know exactly where it is. So it's going to hit at 20, I think. Will it hit at 20? Nope. 8, 16, 24, 36, 40. Nope, first place is going to hit us up there at 40. All right, because it was 8, right? 8 meters per second. Is that right?
Yes.
Yes. So that's the first one it's going to hit a corner on up there. But if it were, you know, to hit a corner somewhere else, if maybe we had changed the velocity, then anywhere it hits one of those corners, that's the best way to do it. Okay, if we've got a graph, because we're gonna end up, once again, it's the slope. Now here's the thing with velocity. We can tell a lot about velocity by which way the slope goes. All right? This is velocity in the positive direction. This is also velocity in the positive direction. All right? Even though it starts down here. If I have velocity in the negative direction, it's going to slope down. All right? Same thing if I start here. Okay, this is velocity in the negative direction.
So you can have like, just make sure, you can have a negative position, but you can't have negative time, right?
Right.
Okay.
That's why there's nothing over here.
Okay, but that's why there's a lot of things.
Yes.
Okay.
Yeah, we can have negative position.
But you can't have negative time.
Can't have negative time. Music is reversible, but you can't go back in time.
I had to think about that for a second.
That's what it says. That if you play it back in the old days, they would backwards mask things on the albums. And of course they would, you know, the thing was always that if you listen to Stairway to Heaven backwards, you would hear a message from Satan. All right? But there were actual songs that had things that were backwards masked into them. And one of them was on one of the Pink Floyd albums. If you played it backwards, it would say the music is reversible, but you can't go back in time.
Yeah.
So, but they actually did backwards mask things onto the albums. But they always said if you listen to Stairway to Heaven backwards, there was a message from Satan. Satan. So don't ever do that. All right? We ruined a lot of record needles trying to hear stuff back in the old days. All right? What if you play it backwards? I don't know. People would freak out. No, don't play it backwards. We'll all go to hell. Let's see. What was number 4? Displacement. All right? And what were we dealing with? Displacement. And we're traveling to the east. And we have a velocity and a time. All right? So up here we have a velocity. All right? On our vertical stem, on our vertical axis. And we have time is always on our horizontal. All right? And we're moving for, let's see, what was our velocity? So this is a velocity graph. So it's 20 meters per second. So when I do a velocity graph, I want to break it up and what is the displacement of a ball traveling east. This is one of the problems. I wouldn't do this on a graph. You can though. All right. So remember, this is velocity. All right. So we'll do it in 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 meters. A little bit high there. 20 meters per second. And it goes for 11 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right. Now, remember, it's a velocity graph. So I plot my velocity, which is 20 meters per second. All right. It travels that velocity for 11 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 seconds. And once again, we run into that. We run into this. Our area, our displacement, is going to be the area of that parallel shape under the graph. All right? So all we got to do now is length times height, and we're going to get the same answer, which was 220. So we've got 220 here, 220, all right, on our graph, because we've got 220 meters per second here, 11 seconds here, 220 meters per second. All right, so it works out the same. Do what?
I got that wrong.
Did you get that wrong?
I think I did. That's the answer?
Yeah.
Well,
Number 4?
Yeah.
Yeah.
Well, I have 9 meters per second to the east.
Yeah, that'd be wrong.
But you put 25 on it.
Did I?
Yeah.
I'd say that's what happens when I'm sleepy. I'm trying to grade these at night.
Because I did 20 minus 11. Because my formula is.
Yeah. No, it should be 20 meters per second times 11.
Maybe I have written down in my notes a dot.
All right.
A minus sign.
Yeah, because again, this is displacement. Displacement is sort of the same thing as what? Distance. All right. So I can use any of my distance formulas as long as I know I've got to have a direction with it. And that direction can be positive or negative, and I've got to designate what it is. And the reason I told y'all to write on there east or west, it might be negative 5 meters east. All right, it wasn't, but I could have that. All right, I could easily have a negative direction. All right. So displacement is just going to be my area under the rectangle. All right. You learned a lot on this last graph. All right. What is the average acceleration of a car which has an initial velocity of 45 miles an hour and a final velocity of 90 miles an hour after 5 seconds? Well, I'm going to kind of draw my graph a little taller. I'm not going to really put a lot of space underneath my origin point. All right. How long did it accelerate for? 5 seconds, so we'll do the half second thing again. 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. So there's 5 seconds right there. All right? All right, so I got 5 seconds. Now I've got 4. I'm starting out at 45 miles an hour. So let's do 5 miles per hour as our velocity over here. And again, this is a velocity graph, velocity versus time. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 90. Well, how fast did that go? 95?
No, 90.
90? Okay. All right. Now, first thing I've got to do is find my initial velocity. So 5, 10, 15, 20, 25, 30, 35, 40, 45 miles per hour. Now, this is not a position. This is a velocity. All right? Now, in 5 seconds, I increase to 90 miles an hour. 5, 10, let's see. 50, 55, 60, 65, 70, 75, 80, 85, 90. All right? So there's my second point. Now, I'm going to come down here and draw my line. All right? Now, I can learn a whole lot from this graph. All right? First of all, what was I asking for? Acceleration. All right?
Yeah.
My acceleration is simply, once again, going to be my slope. Okay? 45 divided by 5 is going to be 9. All right? So my slope here from my position here to my position here is going to give me, if I position it, it's going to give me rise over the run, not my total rise over my run, but my rise from here is going to give me my acceleration. All right? Here's the other thing. Here's a couple of things here. I can tell what my total speed is. Once again, if I use my total rise over my run. All right? If I use my total, I can tell what my total speed is. And the third thing is, I can figure out how far that car traveled during that time. First of all, I've got to know that this is length, okay? Base times height. That'll give me the area for this rectangle. All right? And then if I add to that 1/2 my base times my height here, guess what I'm going to get? Total area that that car traveled in those 5 seconds. All right? So I can get my area, my displacement, by adding those two up. So you can learn a lot. Once you learn to do velocity time graphs and all the uses you have for them, there's a whole lot there that you can use. All right? Anybody got any questions from yesterday?
You want these back?
Yeah, I want them back because I haven't put them in the grade book yet. So I got to have those back. I'll put them in. I guess I'll put them in today. All right, questions? All right, y'all want to watch the video?
No.
Kim Algely, well, you can either do that or write an essay.
I think we'll watch that video. Morgan's not speaking for the whole class.
I didn't speak at all.
You said no.
That was you, I think.
No, Morgan.
Oh, yeah, all right. Y'all listen to me talk all week. I figured y'all listen to somebody else talk for a little while. All right. This is about gravity, and I actually had not seen this, and it's called The Amazing World of Gravity. And it's on YouTube. It's Dr. Kim Algely. And watch that. Had a lot more out earlier. Y'all are all almost all here. But I'll let y'all watch it since everybody else got to.
Are we giving us?
Huh? Yes.
Where do we have to go?
Come back. Picking them up for me. Thank you. Thank you very much.
You're welcome. Can I have a restroom?
Yes.
They're so fancy with the lights.
Yeah.
No.
Huh?
44 minutes. That's a long video.
Well, you're not going to see all of it. We'll watch the rest of it some other time.
Tracy back on?
As soon as Mercedes gets back.
Physics can help. The key to unlocking these everyday questions is gravity. It sculpts the universe. It warps space and time. It's a fundamental force of nature. But gravity's strange powers, discovered by Albert Einstein, also affect our daily lives in the most unexpected ways. In this film, we'll be using cutting-edge scientific techniques to investigate how gravity changes your weight.
It's gone up.
Your height. I really have shrunk, and even your posture. And with the help of thousands of volunteers, I'll show you how gravity makes us all age at different rates.
During the day, I've just been logging onto the phone, logging onto the app.
As a physicist, gravity is central to my work. Oh, wow. And in exploring it, I'll be challenged on how I understand this most mysterious force. Wow. Okay, I have to go write this one down. And I'll have to tackle the very nature of reality itself. Gravity. It binds together all the matter in the universe, and it makes our existence here possible. But in the end, it all boils down to one simple question. What happens if I drop an object? Gravity's many mysteries are all contained in this single action: how an object falls. Here's the first puzzle. Why does a hammer fall faster than a feather? You might think it's because the hammer is heavier, but that's not the real reason. The answer is air resistance. It's not the weight of the objects that matters, it's their shape.
Who's
And I can
in this
demonstrate
class?
very easily with these two umbrellas. They both have exactly
Who's
the same
Mevo in
weight.
this class?
But if I open one of them,
Isaiah.
I'm pretty sure it'll drop more slowly
Who
than
else?
the other one.
Spencer.
That's
In fact, all objects would fall at the same rate if you could only remove the air. The first person to realize this was the 16th century mathematician Galileo Galilei. Famously, it's said he worked it out by dropping objects off the Leaning Tower of Pisa. And he was spectacularly proven right in an experiment carried out on the moon in 1971.
Well, in my left hand I have a feather.
worked perfectly.
How about that? My conclusion, Mr. Galileo was correct in his findings.
Now Galileo was obsessed with a second question too. When you drop an object, it's actually quite hard to tell if it falls at a constant speed or picks up speed as it drops. Even in slow motion, it's pretty hard to tell. But Galileo realized this. First, drop an object a very short distance. It lands with very little impact. But of course, drop it from higher up. This time, the ball easily breaks the tile, which means it must have accelerated, gaining in speed and momentum as it dropped. Galileo had identified something fundamental to all falling objects. They accelerate. He realized there might be a way to measure how much falling objects gain in speed. What he devised was the first ever attempt to measure gravity itself. He built a long wooden ramp, rather like this, that he had sloping at a shallow angle. The idea was to roll balls down the ramp and measure their acceleration. The crucial thing is that the ramp had to be at this shallow angle to reduce the effects of wind resistance. It also meant that the balls would roll down slowly enough to give him time to measure their speed. But the big problem was this: how do you measure time accurately in an age when there were no accurate timepieces, let alone stopwatches? Well, Galileo came up with an ingenious idea involving the flow of water, essentially measuring time from the amount of water collected in a cup. So we're going to try and repeat Galileo's experiment. I say we because I have a couple of willing volunteers, Gavin and Joanna. 3, 2, 1, go. Stop. Okay, there's one. Now, if you come down a quarter of the way down the ramp, go. Stop. Okay, so now half of the way down, go. Stop. Okay, and then 3/4 of the way down, go. Stop. Right, turn the tap off. Okay, so we have our 4 measurements, and I can see a progression from fuller to emptier. But what we need to do now is find a mathematical pattern by weighing carefully the water in each glass. Weighing the water should give us an idea of how long each roll took. And in our experiment, these were the results. Now there's one immediate thing you can tell. The ball really sped up the longer it rolled. In fact, our results seem to show that the time it took to cover the first quarter of the ramp was about the same time it took to cover the next 3/4. Right. So we have a strong hint of a mathematical pattern. Now we'll see if we're right by placing bells along the ramp at intervals which are based on the results. This arrangement looks a bit strange because the gap between the first 2 bells is much shorter than the gap between the 3rd and 4th bells. But that's okay, because if we've got our calculations right, the ball starts off slowly, so it covers a shorter distance, and as it picks up pace, it'll cover longer and longer distances. So we should hear the bells ringing at equal intervals in time. Go. Beautiful. So, what does this all mean? What's the mathematical formula? Well, this is something that Galileo worked out. Let's say, from the start, the ball covers a distance of 1 meter in the first second. After 2 seconds, it'll have covered 4 meters. After 3 seconds, 9 meters. After 4 seconds, 16 meters, and so on. If you recognize this progression, you'll see that distance goes like the square of time. Galileo had found a rate at which gravity speeds up objects. And he'd found another fundamental principle. You can measure the strength of gravity by how much it causes falling objects to accelerate. Detecting gravity has become exceptionally sophisticated these days, but still uses exactly the same principle. This is Hurstmonceau Castle in Sussex, and in its grounds lies the Space Geodesy facility. Here, Vicky uses an astonishingly sensitive instrument to detect the exact strength of gravity on this one spot. Okay, so Vicky, tell me about this incredible gravitymeter that you work with.
Okay, so this is the drop-in chamber in a stripped-down version. So essentially what happens is you've got a cart that gets raised to the top, and then the cart accelerates away from a mass in the middle, and so this section here lifts off, and as it drops under free fall.
So this component in the middle, as it drops, is basically just Newton's apple falling to the ground.
Yes.
So this is a stripped-down version, but that's the real thing.
This is the real thing.
How does it actually work?
In here it's a vacuum.
So there's no wind resistance.
So there's no wind resistance.
Right. Inside, a laser is used to measure exactly how fast the mass is accelerating. This is the 21st century version of Galileo's ramp and the balls rolling down. So can we get it going?
Of course, if you just like to press the button on the laptop.
This one?
Yep.
Okay.
So it's now communicating with it.
Oh, here we go.
There we go. It waits 5 seconds, then takes a measurement of gravity.
And again. Oh, and you can see all the results appearing now.
Yep. Each of those green dots is a measurement of gravity with the actual number that it's getting for each one.
The unit Vicky uses has a familiar ring. I see that the number up at the top here. So you've got this unit, microgal.
Yes, gal is essentially 1 centimetre per second squared. The gal was named after Galileo.
So we've just taken the measurement of gravity here today, and it's this highly accurate number, 981124007 microgals. The reading means that the Earth's gravity speeds up a falling object by around 9.81 meters per second for every second it drops. Vicky tells me something intriguing. She takes a reading here every week, and she's found that the strength of gravity changes by tiny amounts over time. Heavy rainfall, for example, can cause gravity to increase slightly. Presumably, if gravity is changing here in one spot, it will have different values all around the world, and so you can have a gravity map of the entire planet.
That's right, yeah.
So what's the reason for these strange fluctuations? That's what I want to investigate next. So, gravity changes as we move across the surface of the Earth. Well, this lies at the heart of a challenge that I've set 2 young volunteers. I've given them a task to try and find a place in Britain where gravity is at its weakest, so where objects would weigh the least. And I've given them just 3 days to try and find it. The volunteers are Estrella Sendra, a PhD student.
I've been living in London for 5-6 years, and I'm originally from Seville in Spain. I'm very interested in taking part in this project because I would really like to know more about how this world works.
And Poppy Begum, a journalist who lives in London.
I did my degree in biomedical science, and I did biology and chemistry for my A-levels, but I haven't done any physics since I left school. I'm fascinated to find out more about gravity, and I actually enjoy a puzzle. I like a challenge.
Now, the team can't just weigh themselves to see changes in gravity. Body weight fluctuates naturally by a couple of kilos over the course of the day, whereas changes due to gravity as they travel around the country are going to be tiny in comparison, a matter of a few grams. So they're going to have to use sophisticated scientific methods if they want to measure gravity accurately. And that's why the volunteers will be joined by 3 specialists in gravity science. PhD student Sonak Bose, He'll be in charge of some very sensitive measuring apparatus from the National Physical Laboratory. Sean Hughes, a geologist, who'll be using a portable gravity meter. And Andrew Ponson, a cosmologist at University College London, who'll help interpret the results. We've taken a collective weight for the team before they set off. It's 380 kilograms. So, can they find the place in Britain where that'll decrease? They're setting out in Snowdonia National Park in North Wales. The railway climbs from here to the 1,000-metre summit of Snowdon. Sean takes his first gravity reading.
The inside is a mass on a beam, and you turn this counter, this dial, until you get the beam central.
By counting the number of turns of the dial, Sean can calculate the downward pull of gravity acting on the mass inside the machine. Sonak has a simpler method.
So inside the box is a 2 kilogram mass, and it's supposed to be sort of as perfectly 2 kilograms as it's possible to get. Alright, and place it here.
Oh, this is coming under, isn't it?
1998.2 grams.
So it was 2 kilos in the laboratory, but now here it's a bit less.
It's the first puzzle. Why does a 2 kilo mass tip the scales at just under 2 kilos? And it's one which gets straight to the heart of what the challenge is really about. Mass is often confused with the related quantity, weight. The mass of these dumbbells is fixed, it doesn't change. It's a measure of how much stuff they contain. Weight is different. It's a measure of the effect of gravity on these dumbbells, the downward force pulling them to the ground in the same way that it's keeping my feet firmly stuck to the ground. The crucial difference is this: if I was holding these dumbbells on the moon, they'd still have exactly the same mass, but they would weigh 6 times less because the moon's gravity is so much weaker than the Earth's. So that's why Sonak's bringing along the 2 kilo mass. If it changes weight, then this should mean that gravity itself has changed. Ahead of them is the summit of the highest mountain in England and Wales, famed for its stunning scenery. Or it would be stunning if you could see it.
And this is what we came all the way up here for, this amazing view at the top of Snowdon. You wouldn't know it, but honestly, we are here. So we're now near the summit of Snowdon, and I've set up the gravimeter again, and we're going to see what the difference in the reading is.
He has to turn the dial again and again to try and get a reading. It's clear gravity has changed, but which way? Has it got stronger or weaker? The team leaves Sean to work out his results and tries to position the scales as close as possible to the summit. But the reading is all over the place.
Oh,
It's gone up.
it's fluctuating quite a lot due to the wind.
I have to say, this is what science is always like, isn't it? It's never quite what you want it to be.
So they head inside to the cafe next to the summit.
The wind was being a bit naughty, but hopefully...
Now it's in 0, so it should be alright.
1998.2 down there. 1997.8. We've got it.
That's 0.4 for gram off.
The mass weighs a tiny bit less. It's lost about 1/5000th of its weight. And Sean's found that gravity itself has reduced.
At the top of the mountain, we took the measurement, and we discovered that the pull of gravity had gone down. It had gone down an equivalent of 206 turns of the dial, and we worked out that that's equivalent to 219 milligallons.
So it's clear from the team's measurements, gravity weakens as you go higher, and you get a bit lighter.
It's just an excuse to say where are we like the lightest, who cares? But in the sense that it's actually really interesting. It's like an illustrative example of seeing how this
is actually fluctuating depending on different factors.
Yeah, absolutely. And that we could measure it and we could see it with our own eyes. It actually makes you think about gravity in a very active way. It's such a fundamental force phenomenon in nature, but we don't know that much about it.
But why does gravity change with altitude? To understand that question, you have to get to grips with the extraordinary discoveries of the next scientific giant in our story, Isaac Newton.
Alright, Vikings, a couple announcements before
Born in England in the middle of the 17th century,
There
spent
is
his life
a mock
wrestling
trial
with so
interest
many
meeting after school
apparently
today in
separate
the
questions.
Media Center. If you'd like to participate in mock trial, please attend. Also, tomorrow from 3 to 4, there is Seneca Choices for Life. If you'd like to participate, please speak to Mr. Chartis. Don't forget, tomorrow there is the University of Tennessee, Columbus State University, and Purdue University. If you'd like to participate in this virtual college